Welcome to another deep dive. Today we're going to be talking about polynomial optimization on the unit sphere.
Yeah.
For our listeners who love math, this is going to be a good one. We'll be looking at convergence analysis for some approximation techniques,
Right.
like the Moment-sos and spectral methods. And it's just so cool how tools like the polynomial kernel method and, matrix symmetries all tie into this.
It is. I mean, it's really amazing how these different areas all come together.
Okay, so let's set the stage here. We are trying to minimize a polynomial, right?
Mm-hmm.
But it's on the unit sphere.
Yes.
Which, if you look at page 1 of the source material, we can represent that by the equation P-min APSU XTR N acres O2 E2.
Right.
So how are people, like researchers approaching this? How are they trying to solve this problem?
Well, there are two main methods that kind of stand out.
Okay.
You have the Moment-sos Approach,
Wow.
which uses semidefinite programming and gives you these semidefinite bounds. And then you have the Spectral Approach, which was developed by Lovitz and Johnston,
Mm-hmm.
and that uses eigenvalue computations and produces what we call spectral bounds.
Got it.
Now, the Moment-sos, it tends to be a little more computationally heavy, but it also can give you really strong bounds.
Okay, so more work, but better results, potentially.
Exactly. And then you have the spectral method, which is much easier computationally,
Mm-hmm.
but the bounds it produces might not be as tight.
Okay, so there's like a trade-off there.
Yeah, like most things in life.
Right. So can you break down these two approaches a bit more? Like, how do they actually work, methodologically speaking?
Sure. So the Moment-sos approach, well, it all starts with the concept of sum of squares polynomials. We essentially want to represent the polynomial, after a bit of manipulation involving this constant lambda, as a sum of squares.
Right.
Because, and here's the key, any polynomial that can be expressed as a sum of squares, it has to be non-negative. That's really important. So we use that fact to establish a lower bound. The largest lambda that allows for this sum of squares representation is what gives us that bound. We call it sort.
Okay, I see. So that's where the equation SO SRDP Ozanda SO comes in. It's all about finding that maximum lambda.
Exactly. It's got to maintain that sum of squares structure.
Gotcha. And what about the spectral approach? What's going on over there?
So the spectral approach, it's kind of a different beast. We construct specific matrices related to the polynomial and that unit sphere constraint we were talking about.
Yeah.
But these matrices, they have to be doubly symmetric.
Okay.
And it turns out that this double symmetry allows us to use the smallest generalized eigenvalue of these matrices to get our spectral bound.
Okay, so to summarize, Moment-sos is all about sum of squares and semidefinite programming, whereas spectral uses eigenvalue computations on these special matrices.
Yeah, that's a good way to put it.
Great. Now, how fast do these methods actually converge to that minimum value? What can we say about their convergence rates?
Right, that's an important question. So the Moment-sos method, it has a convergence rate of OR. This quadratic convergence, it was actually shown in the work of Fang and Fauzi, and it's quite impressive.
Okay, so that means the error shrinks quickly as we increase the level of the hierarchy, right?
Yes, exactly. Very efficiently.
And how does the spectral method compare in terms of convergence?
So the spectral method, according to Lovitz and Johnston, it achieves a convergence rate of ORR. It's linear, which is a bit slower than the Moment-sos, but still quite good for many applications.
Right. Now, this is where things get really interesting for me. I understand that the quantum to Finetti theorem, that concept from quantum information theory, comes into play here.
Yes. It's surprising, isn't it?
It is. How is something from the quantum world connected to this, classical polynomial optimization problem?
Well, the quantum to Finetti theorem, it's essentially a tool for approximating these complicated quantum states, especially entangled ones, with a mixture of simpler separable states. It's really helpful when you're dealing with systems that have strong correlations between, their individual components, because direct analysis can get really tricky.
So does that mean this theorem helps us understand how well these methods approximate the true minimum value on the unit sphere?
Yes, exactly. It provides a framework for analyzing that convergence. But there's a catch. The original quantum de Finetti theorem, the one we use in quantum information theory, it applies specifically to complex Hermitian matrices.
Right.
So since we're working with real-valued polynomials and matrices in our optimization problem, we can't just directly apply the quantum version.
So the question is, does a real analog of the quantum de Finetti theorem exist?
Exactly. That's what researchers have been trying to figure out. And it turns out that a direct analog, at least for real matrices with the same double symmetry property, it doesn't actually exist.
Oh, so there's a roadblock. We can't just translate it directly from the quantum world.
Right.
Is there an example that shows why this direct analog fails?
There is. If you look at page 12, you'll see this family of matrices. R12, UUR, plus 12, VV, where U1, I2, and V1, I, it's a through 2, 2.
Okay.
It's based on work by Caves et al. These matrices, they're real, they're doubly symmetric, and they're positive semi-definite. But they can't be approximated effectively by real separable matrices, like a direct quantum de Finetti analog would suggest.
So that family of matrices really throws a wrench in things, huh?
It does.
So does this mean all hope is lost? Are there any real de Finetti-like theorems that we can use, maybe ones that work with different symmetry conditions?
Well, there is some good news. There are actually a couple of real de Finetti type theorems that come into play here. The first one was developed by Doherty and Weiner.
Okay.
And it applies to real matrices, but with a stronger symmetry condition.
Really stronger.
Instead of just double symmetry, it needs maximal symmetry.
Okay, and how is maximal symmetry different from double symmetry?
So double symmetry, the rows and columns are interchangeable, right? Maximal symmetry, it goes a step further. There's a deeper level of symmetry in the actual entries of the matrix.
Okay, so it's like double symmetry, but even more symmetrical.
Yes, exactly. And for these maximally symmetric matrices, Doherty and Weiner's theorem does provide a real analog to the quantum de Finetti theorem.
Oh, that's great.
And it allows for approximation with an error bound proportional to 1R.
So that's one option. You mentioned there was another real de Finetti type theorem too, right?
Yes, there is. And this one's actually something I've been working on.
Oh, wow.
I call it a banded real de Finetti theorem. It applies specifically to those real doubly symmetric matrices, the ones that the quantum version couldn't handle directly.
Interesting. Does it give a direct approximation of the partial trace, like the quantum de Finetti theorem?
Not quite. Instead of approximating the partial trace directly, it approximates the maximally symmetric projection of the partial trace.
Okay.
It basically shows that you can approximate this projection by a scaled, real, separable matrix.
So it's kind of a modified version tailored to handle these specific symmetries we're dealing with.
Yeah, exactly.
What's the error bound like for this approximation?
So the error bound is proportional to the square root of this specific dimension. We call it NNENANA divided by R plus 1, where R is, the level of our hierarchy.
Right.
If you look on page 13, you can see the full equation.
Got it. So we've got a couple of real de Finetti type theorems in our toolbox now, which is great. And I noticed that the research paper talks a lot about the polynomial kernel method being used to analyze the convergence of the Moment-sos method. Can we use that same technique with these real de Finetti theorems we've been talking about?
You absolutely can. In fact, I've already been exploring that.
That's awesome. Did you find any improvements in the convergence rates?
I did. So by using what's called the adjoint polynomial kernel operator, I was able to actually enhance the convergence rate of Doherty and Weiner's theorem for those maximally symmetric matrices.
Wait, so you improved their theorem?
I did.
Did you manage to get it from O1R to O1R?
Yeah, it's now O1R. It converges much faster now, which is really exciting.
That's amazing. That's a fantastic result. So we've looked at these real de Finetti theorems and even found ways to make them better.
Right.
What about the spectral hierarchy? Any chance we can improve its O1R convergence rate?
So this is where things get interesting again. I've actually found a complexity lower bound for the spectral hierarchy, and it's 8AR.
ARR. So that means it can't converge any faster than that, right? What was the key to finding this lower bound?
Yeah, you can't go any faster than that. And the key is this really interesting form called the Choi-Lam form.
The Choi-Lam form. I'm not familiar with that one. What's so special about it?
Well, it's special because it's non-negative, but it's not a sum of squares.
Okay.
And that's crucial for establishing this complexity bound. If you flip to page 18, you can see the equation for the Choi-Lam form. PCLX by 12 by 22 plus by 12 by 32 plus by 22 by 32 plus by 44, 4 by 1 by 2 by 3 by 4.
So this Choi-Lam form, it really reveals some fundamental limitations, huh?
It does. It shows that the spectral hierarchy, it can't converge faster than O1R, like no matter what we do.
Does that lower bound match the current upper bound for the central method?
Not exactly. There's still a gap between the current upper bound of O1R and this new lower bound of OR.
So there's still room for exploration there. This is really exciting. We've covered so much ground, but it feels like we're just scratching the surface.
Yeah, it's a very active area of research. There's a lot more to discover.
This has been an amazing journey so far. We've talked about the Moment-sos and spectral methods, delved into quantum information theory, and even uncovered some really cool complexity bounds.
Absolutely. It's been a great discussion.
But there's still so much more to explore, and we're just getting started. Stay tuned for part 2 of this deep dive, where we'll take an even closer look at the Moment-sos approach.
Looking forward to it.
Welcome back to our deep dive.
It's great to be back.
We've covered a lot of ground already, talking about, minimizing polynomials on the unit sphere, those two key methods, Moment-sos and spectral.
Right.
And how that quantum Finetti theorem surprisingly comes into play.
And those real analogs, too.
Exactly. So now I'd love to dig deeper into the Moment-sos approach specifically. It's just such an elegant method.
It really is. It's a great example of how, abstract math can have very real applications.
Okay, so let's remind ourselves of the basic idea here. We're essentially trying to build this hierarchy of lower bounds for the minimum value of the polynomial, right?
Yes, exactly. So we have 15, the minimum value, and the Moment-sos approach gives us a sequence of increasingly tighter lower bounds, which we denote as SOS, right? Where R is the level of the hierarchy.
Right. So as we go higher in the hierarchy, we get closer and closer to the actual minimum. But how do we actually construct these bounds? I know it involves some of squares, polynomials, and some clever manipulations.
Yeah, so the core of the Moment-sos approach is about representing the polynomial after a specific transformation as a sum of squares.
Okay, so we're expressing the polynomial as a sum of squared terms. Why is that so important for getting these lower bounds?
Well, the key is that any polynomial that can be written as a sum of squares has to be non-negative. That non-negativity is what allows us to get the lower bound. Think of it this way. We subtract a constant lambda from our polynomial, and if we can represent what's left as a sum of squares, then the original polynomial must always be greater than or equal to lambda.
I see. So lambda is essentially a lower bound for the polynomial's value.
Yeah.
And we're trying to find the biggest lambda that still lets us have that sum of squares representation.
Exactly. And that's what the equation is max to RP, max to RDP is all about. It's finding that maximum lambda while maintaining the sum of squares structure.
Right. It's all about that structure. But how do we actually find this sum of squares representation in practice? It's all, again, a bit abstract for me.
That's where semidefinite programming comes in. It's this really powerful optimization tool that lets us search for positive semidefinite matrices that satisfy certain constraints.
Okay. Constraints. What kind of constraints are we talking about here?
Well, the constraints make sure that the matrix we find actually represents our polynomial, minus the lambda, while still having that sum of squares structure. It's a delicate balance, but semidefinite programming is really good at handling it.
So we're using semidefinite programming to find a positive semidefinite matrix that represents our polynomial in this special way. And the biggest lambda we can use in that process gives us our lower bound. Is that right?
You got it. The Moment-sos approach is this beautiful blend of algebra and optimization.
I can see the beauty, but it definitely takes some mental gymnastics. So we've talked about the convergence rate of the Moment-sos approach, O1, R2. What does that actually mean practically?
Well, it means that as we go higher in the hierarchy, R gets bigger. The difference between our calculated lower bound SOS and the true minimum, P-min, it shrinks really fast, quadratically, in fact.
Quadratically. So like if we double the level from, say, R to 2R, the error would decrease by a factor of 4.
Exactly. That's the power of quadratic convergence. It's a big advantage of the Moment-sos method because it means we can get accurate estimates without having to go too high in the hierarchy.
That's amazing. But I'm sure there's still some limitations, right? No method is perfect.
You're right. There's always a trade-off. As R increases, the size of the matrices involved, they grow really quickly, and that makes the semi-definite programs much harder to solve, so it can get computationally expensive.
So there's that balance again, accuracy versus computation.
Exactly. If we want more accuracy, we need more computational power, and sometimes it might be better to settle for a lower level in the hierarchy to keep things manageable.
Makes sense. Practicality is important. Now, we've been talking about the Moment-sos approach in general. Are there any real-world examples of how this method is actually used?
Oh, tons. The Moment-sos approach is used in all sorts of fields. Control theory, robotics, signal processing, finance, you name it. Anywhere you need to optimize systems with polynomial dynamics or constraints, the Moment-sos approach can be a powerful tool.
So, like, if we're dealing with robots or financial models, the Moment-sos approach could be helpful.
Absolutely. Let's say you're working in control theory. You could use Moment-sos to find the optimal inputs to, say, steer a system to a desired state while minimizing energy use.
Wow, that's really cool. It's amazing to see how abstract math can have such tangible applications.
It really is. And as research continues, I'm sure we'll find even more uses for the Moment-sos approach.
So we've covered a lot about the Moment-sos approach in this part, but there's still another fascinating method for polynomial optimization on the unit sphere we need to talk about, the spectral method.
Right.
Join us in part 3 as we explore the ins and outs of that approach. And we're back for the final part of our deep dive.
Time flies when you're talking about math.
It really does. So we've been exploring polynomial optimization on the unit sphere, right?
Right.
We did a deep dive on the Moment-sos approach.
Which is super powerful.
It is. But remember, there's that other method, the spectral method.
Yes.
What?
A bit more computationally friendly.
Exactly. So let's talk about how this spectral method actually works. What are the main ideas behind it?
Well, the spectral method is all about eigenvalues. Really elegant, actually. Instead of those complicated semi-definite programs, we just construct specific matrices related to the polynomial and the unit sphere constraint.
Matrices again. Seems like we keep bumping into matrices.
We do. Both methods use them, but in different ways.
Okay, so how do we build these matrices for the spectral method?
Yeah.
Any special properties they need to have?
They have to be doubly symmetric. Remember when we talked about those real Finetti theorems?
Yes. Double symmetry rows and columns can be swapped.
Exactly. So we create these doubly symmetric matrices that represent our polynomial and that unit sphere constraint.
And then I bet the eigenvalues come in.
You got it. We compute the smallest generalized eigenvalue of that matrix.
And that's our spectral bound.
It is. A lower estimate for the true minimum.
So much simpler than those semi-definite programs.
Definitely. Eigenvalue computations are generally faster, especially for large problems.
Makes sense. Speed is key in the real world. Now, we've talked about using techniques like the polynomial kernel method to improve those real Finetti theorems. Could we do something similar with the spectral method to get a better convergence rate?
That's a great area for future research. The lower bound of error tells us we can't go faster than that.
Right.
But there might be ways to tweak things, maybe with different polynomial kernels to get closer to that lower bound.
So there's still room for improvement. That's what I love about math. There's always something more to explore. It's been amazing diving into these methods with you.
Likewise. The connections to quantum information theory, it's all fascinating.
It really highlights how everything's connected in math.
Absolutely.
So to our listeners, I hope you've enjoyed this deep dive as much as we have. It's been a whirlwind tour of polynomial optimization on the unit sphere.
We've seen powerful methods, connections to quantum information theory, and even glimpsed some exciting real-world applications.
And hopefully this has sparked your curiosity to delve even deeper into this incredible world of mathematics.
There's so much more to discover out there.
Thanks for joining us, and we'll catch you on our next deep dive into the fascinating world of math. All right, so you've brought this research paper, Moment-sos and Spectral Hierarchies for Polynomial Optimization on the Sphere and Quantum Finetti Theorems.
Yes.
So, looks like we're going really deep with this one, huh? Some pretty high-level math concepts going on in here.
Definitely, yeah. We'll be looking at how we can use these methods to try and minimize a polynomial on a sphere.
Okay.
And, this isn't just some theoretical math problem. It pops up in all sorts of fields, computer science, economics, engineering.
So finding the minimum value of a polynomial on, like, the surface of a sphere.
Yeah.
Okay. I mean, at first glance, it sounds kind of simple, but I have a feeling it's way more complicated than that.
Oh, you're absolutely right. Yeah, finding the exact minimum directly, that can be a nightmare. It's really tough.
I bet.
And that's why mathematicians have come up with these clever approximation methods like the Moment-sos and spectral hierarchies.
Okay, so these hierarchies, is that like a series of approximations to get more and more accurate?
Exactly. You can think of them as steps, and each step kind of refines the one before it.
Okay.
And so you get closer and closer to the true minimum of the polynomial on the sphere.
I see.
The level R tells you how complex the approximation is.
Okay.
The higher the R, the more complex it is, but usually that means you get closer to that true minimum.
All right. And you mentioned the Moment-sos method. What's that about?
Moment-sos, which stands for moment sum of squares, uses this really interesting relationship between moments and sums of squares.
Okay.
Moments are all about capturing the spread of a polynomial's values on that sphere. And sums of squares, well, they guarantee that a polynomial stays non-negative, meaning it never goes below 0.
So moments tell us about the spread, and sums of squares make sure it doesn't dip below a certain point.
Precisely. And the really cool part is there's this deep connection between these two concepts. It's called duality, and it's a really important principle for analyzing and solving optimization problems.
So moments and sums of squares are connected by duality. And we can use that to build these hierarchies that get us closer and closer to the actual minimum.
Exactly. And this research paper, it digs into how quickly these hierarchies converge.
Right.
How quickly they get to the true minimum as you increase the level that R.
Gotcha. You mentioned the spectral method, too. How is that different from the Moment-sos approach?
They both aim to approximate the minimum, but they use different techniques. Moment-sos uses semidefinite programming, which is a powerful optimization tool that takes advantage of the properties of sums of squares.
Okay.
The spectral method relies on eigenvalue computations. It draws from linear algebra.
So different tools for the same job. What about the convergence rates for these two methods?
Well, the paper establishes upper bounds. For the Moment-sos method, the error decreases at a rate of O1R2.
O1R2.
Which means the error shrinks quadratically as you increase R.
Right.
And for the spectral method, it's O1R, so a linear decrease.
So just looking at the bounds, it seems like the Moment-sos method converges faster.
That's what the analysis suggests,
Yeah.
But remember, these are just upper bounds. The actual convergence rates could be faster, especially for the spectral method.
Interesting.
One of the open questions is whether we can find tighter bounds to close that gap between theory and what actually happens.
So there's like this unknown territory within those bounds where the true convergence rate might be hiding.
Right. And that's one of the things that makes this research so exciting,
Yeah.
We're not just learning what we know, but we're also trying to figure out the limits of what's even possible.
Okay. Let's talk about quantum mechanics for a second.
Yeah.
I have to admit, when I saw quantum de Finetti theorems in the title, I was a bit intimidated.
Yeah, I get that. It sounds pretty complex.
Yeah.
But the main idea behind them is actually quite intuitive.
Okay.
These theorems come from quantum mechanics, and they offer a powerful way to take complex quantum states and approximate them using simpler building blocks.
So breaking down a complicated thing into smaller, easier to understand parts.
That's a good way to think about it. And the amazing thing is that these quantum de Finetti theorems, they've popped up in polynomial optimization. They give us tools to approximate those complex objects we deal with when minimizing our polynomial and to represent them in a simpler way.
Okay, so we're using these quantum ideas to make our polynomial problem easier to handle.
Exactly. The paper talks about two types of these theorems. One for doubly symmetric matrices and another for maximally symmetric matrices. They represent different aspects of our polynomial, and the theorems tell us how well we can approximate them.
Hold on, can we break down those matrices, the doubly symmetric and maximally symmetric ones? What are they and why is the difference important?
Sure. A doubly symmetric matrix is symmetric across both of its diagonals.
Okay.
So imagine folding it in half both ways, and the numbers match up perfectly.
Okay, I can picture that.
A maximally symmetric matrix is even more symmetric. It doesn't change no matter how you shuffle its rows and columns.
So doubly symmetric matrices have a specific order, and maximally symmetric ones are symmetric no matter how you rearrange them.
Got it. But how does this difference actually affect our optimization problem?
Well, the difference in their symmetry leads to different kinds of approximation guarantees from those quantum de Finetti theorems.
Okay.
So for doubly symmetric matrices, we get one set of bounds, and for maximally symmetric ones, we get another set.
Right.
And those different bounds actually influence how we analyze the convergence of the spectral method.
So the type of symmetry affects how well our spectral method works, and these quantum theorems help us quantify that impact.
That's right. It's a really cool example of how a seemingly abstract concept from one area of math can actually have a real impact in a completely different area.
Now, you also mentioned a real version of the quantum de Finetti theorem.
Right.
What's that all about? I mean, aren't all numbers real?
It's a good point, and it highlights a subtle difference. The original quantum de Finetti theorem uses complex numbers, which are very common in quantum mechanics.
But for our polynomial problem, we mostly care about real numbers.
Okay.
So mathematicians came up with these real versions of the theorems specifically for those real-valued problems like ours.
So it's like we're taking a tool from quantum mechanics, adapting it to our world of real numbers,
Yeah.
and then using it to solve this challenging optimization problem.
Exactly. And the paper dives into how these real de Finetti theorems differ from their complex versions and how we can use them to analyze the spectral hierarchy in our situation.
Okay. Now, earlier you mentioned the bandit approach. What's that all about?
Ah, the banded approach. That's a neat trick the researchers came up with to analyze these real doubly symmetric matrices more efficiently.
Right.
Instead of trying to approximate the whole matrix, they just focus on specific parts, like bands within the matrix.
So instead of tackling the whole problem at once, they zoom in on the most important parts. What's the benefit of focusing on these bands?
Well, it makes the analysis much simpler. We can figure out the O1R convergence rate for the spectral hierarchy directly without having to use those complex optimization techniques that need complex numbers.
So it's a simpler and more direct way to reach the same conclusion, staying within the realm of real numbers.
Exactly.
Why put in all this effort to analyze these different methods and their convergence rates? What's the end goal?
The ultimate goal is to understand what's possible, where the limits lie. These researchers don't just want to analyze how these methods work.
Yeah.
They want to know if we can do better.
Right?
Are there fundamental limitations to how quickly these methods can converge? Are we pushing the boundaries of what's computationally feasible?
So they're not just climbing one mountain, they're looking for even higher peaks to conquer.
Exactly. And to explore those limits, they look into complexity lower bounds.
Okay.
These are mathematical proofs that tell us the limits on how fast any algorithm can solve a problem, no matter how clever the algorithm is.
It's like a speed limit, saying you can't go faster than this, even with the most powerful computer you can imagine.
Exactly. And to show this, they use a special polynomial called the Choi-Lam form.
Okay, I'm intrigued. What's special about this Choi-Lam form? What makes it different from other polynomials?
The Choi-Lam form is unique because it's always non-negative, so it never goes below 0, but you can't write it as a sum of squares.
Huh, that's interesting.
It's kind of counterintuitive because
Yeah.
we think of sums of squares as the way to guarantee non-negativity, but the Choi-Lam form breaks that rule, which makes it really fascinating.
It's a rebel in the world of polynomials, breaking the rules.
Right. And because it can't be written as a sum of squares, it shows us a limitation of the Moment-sos hierarchy. Remember, Moment-sos works by finding those sum of squares representations.
Right.
So if a polynomial can't be represented that way, the Moment-sos method hits a wall.
So the Choi-Lam form is like a trap for the Moment-sos method, revealing its limits.
Exactly. By looking at how the Moment-sos and spectral methods work with the Choi-Lam form, the authors prove that the convergence rate can't be better than -1R2.
So we hit a speed limit, a barrier we can't break with these methods.
Right, and this emphasizes the importance of understanding not just what our tools can do, but also what they can't do. Knowing these limits can help us find new, better methods.
This is all fascinating, but my head is spinning a bit with all these concepts. Moment matrices, sum of squares, quantum de Finetti theorems, complexity lower bounds.
I understand. It's like we've climbed a mountain of math concepts, and the view is amazing, but also a little overwhelming.
Exactly. Could we take a step back and review some of those core definitions before we move on? It would be helpful to have a solid grasp of the basics before we build on them.
Absolutely, a great idea. A good foundation is key to appreciating all the details of this research. Let's start by revisiting those doubly symmetric matrices we talked about earlier.
All right, that sounds good to me. All right, a recap of those doubly symmetric matrices would be helpful.
Sure.
You mentioned they have a specific kind of symmetry. Can you explain that a little more?
Of course. A doubly symmetric matrix has, as the name suggests, two types of symmetry. It's symmetrical along both of its diagonals. So if you swap any two rows and then swap the corresponding columns, the matrix stays the same. It's also invariant under projections from higher dimensional tensor spaces.
So it's like a mirror image, both horizontally and vertically.
Yeah.
Okay, makes sense. You mentioned maximally symmetric matrices too, right?
Yes.
How do they differ from the doubly symmetric ones?
Maximally symmetric matrices have even more symmetry. They stay the same, even if you shuffle the rows and columns any way you want. Think of it like, shuffling a deck of cards.
Okay.
No matter how you rearrange them, it's still the same deck. Mathematically, this connects to the symmetry of the underlying tensors that represent these matrices.
All right, so doubly symmetric matrices have a specific order, while maximally symmetric ones are symmetric no matter how you rearrange them.
Right.
Got it. Now, the paper also talks about representing matrices for polynomials.
Yes.
Can you unpack that a little?
Absolutely. Basically, every polynomial can be associated with a unique matrix that kind of captures its coefficients and structure. This link between polynomials and matrices allows us to use all these powerful tools from linear algebra to analyze and manipulate the polynomials.
So we're translating a problem from the language of polynomials to the language of matrices.
Exactly.
And we have better tools in that language.
Yes. Now, another important concept is that of linear functionals.
Okay.
You can think of them as measuring sticks for polynomials. They take a polynomial and give you back a single number telling you something about the polynomial's overall behavior.
So instead of looking at each term in the polynomial, a linear functional gives us a single value that represents the whole polynomial.
Precisely. It lets us look beyond the individual terms and see the global properties. And these linear functionals are closely related to those moment matrices we talked about before.
Yeah.
Remember how we said that moment matrices capture information about the distribution of a polynomial's values on the sphere?
Yes, it's like taking snapshots of the polynomial at different points on the sphere and then putting all that information together into a matrix.
Exactly. And it turns out that linear functionals and moment matrices are very closely related.
Okay.
You can actually think of a moment matrix as a way to represent a specific linear functional.
So we have all these layers.
Mm-hmm.
Polynomials represented by matrices, measured by linear functionals, which are then connected to moment matrices.
That's right.
That's all very intricately connected.
It is. But as you said, each layer provides a different perspective, a different tool for understanding these polynomials and how they behave.
Okay, that makes it much clearer. Now, I want to get back to the main problem in the paper, minimizing a polynomial on a sphere. All these definitions and concepts, are they all tools to help us tackle this problem?
Absolutely. We need to understand these concepts to really appreciate how elegant and deep these methods in the paper are.
And the cool thing is that these seemingly abstract mathematical ideas have real-world applications.
Yeah.
Like we said, these techniques can be used in engineering, computer science.
Yeah.
But are there other areas that could benefit from this kind of research?
Oh, the possibilities are huge. Take machine learning, for example.
Okay.
At its heart, it's all about optimization, finding the best parameters for a model to make accurate predictions.
Right.
The techniques discussed in the paper, especially the analysis of complexity lower bounds, they could help us design better machine learning algorithms, algorithms that are faster and more efficient.
So this research could help us build smarter, more efficient AI.
Absolutely. And it's not just computer science.
Oh, else.
Fields like statistical physics, signal processing, even economics, they could all benefit. Anytime you're dealing with complex systems that need optimization, these tools could provide new insights and solutions.
So it's like we're developing a new way of looking at problems that were too difficult to solve before.
Right.
Now, the paper also talks about the limits of these optimization methods. Does that mean we've hit a ceiling? Are we getting to a point where we can't improve these techniques any further?
Well, it's important to keep in mind that the paper focuses on specific methods, and the lower bounds they find are for those particular methods.
Right.
These bounds tell us something important about the limitations of these approaches, but that doesn't necessarily mean there's a hard limit on optimization as a whole.
So even though we've hit some limits with these specific methods, there's still room for improvement.
Exactly. There might be completely new optimization approaches out there that we haven't even discovered yet, approaches that could get around these limitations.
Okay.
Or maybe there are ways to tweak the existing methods to make them work better for certain types of problems.
It's not a dead end. It's a challenge to find new and more innovative solutions.
Precisely. And that's what's really exciting about this research, pushing the boundaries of what's possible, exploring new mathematical ideas, and maybe even changing how we think about optimization altogether.
So where do we go from here? What are the next steps for mathematicians exploring these ideas?
There are several promising directions. One obvious one is to try and tighten those convergence bounds.
Right. Remember how we talked about how the actual convergence rates might be faster than the upper bounds in the paper?
Yeah.
Like knowing a car can go at least 60 miles per hour, but thinking it might be able to go much faster.
Exactly. So we need to develop better analytical tools, more precise ones,
Okay.
to really pin down those true convergence rates. Maybe we need to explore new mathematical tools or find clever ways to use the specific structure of these problems to our advantage.
So we need to fine-tune our instruments to get a better reading of these methods. What other directions could this research take?
Another interesting avenue is to see if these techniques can be applied to a wider range of problems. The current work focuses on minimizing polynomials on a sphere, which is pretty specific.
Right.
But what if we want to optimize different kinds of functions, maybe more complicated ones, over more general sets?
So expanding the toolkit, so to speak.
Right. Think about using these techniques to optimize complex systems in biology, like modeling the interactions within a cell or simulating evolution. Or maybe we could design more efficient energy grids, taking into account all the complexities of energy sources and distribution. We could even model the dynamics of social networks, how information spreads, and how communities change over time.
Those are some pretty big possibilities. Sounds like there's a lot of potential here.
Definitely.
Now, I want to touch on the computational aspect of this research. These optimization methods seem to rely heavily on computers to do the heavy lifting, the calculations.
You're absolutely right. The Moment-sos and spectral hierarchies are elegant in theory, but as the problems get more complex, they can become very demanding computationally.
So there's a balance between accuracy and the computing power you need.
Exactly. And that brings up another area of research, developing more efficient algorithms for these optimization methods.
Okay.
Maybe we can explore new computational paradigms like parallel computing or even quantum computing.
Quantum computing, now that sounds really futuristic.
It is cutting edge, but quantum computers have the potential to revolutionize certain types of calculations, especially those involving optimization. They leverage the principles of quantum mechanics to do things classical computers simply can't, which could lead to much faster solutions for some problems.
So we have these theoretical limits on how fast these methods can converge, but the way we actually run them on different computers also plays a big role.
Absolutely. It's not just about the math, it's about how math and computation work together. We need to find ways to make these powerful tools practical for real-world problems.
It's really interesting to see all these different fields, math, computer science, even quantum physics, coming together to solve these really tough optimization problems.
It really shows how interconnected knowledge is. Progress in one area often leads to advancements in others, and that can lead to unexpected breakthroughs, a deeper understanding of the world.
Well, I think we've covered a lot in this deep dive. We've explored the Moment-sos and spectral methods, quantum Finetti theorems, and even the limits of what computers can do.
It's been a great discussion, and I'm particularly excited about those open questions we've uncovered. There's still so much more to explore in this field.
It's reassuring to know that even in such a complex area of math, there's still room for new ideas and breakthroughs.
Yes.
It reminds us that learning is a continuous journey.
Absolutely. And I think the tools and techniques we've talked about today will be really important in shaping that journey, leading to new discoveries and solutions to some of the biggest challenges we face.
Well, I think we've reached the end of our deep dive.
Yes.
Thanks for joining me on this intellectual adventure.
Thanks for having me.
Until next time.
Okay, yeah. So let's step back a bit and think about the bigger picture.
Yeah.
What does this research really mean? You know, we've been talking about all this heavy-duty math.
Yeah.
But how does it connect to the real world?
Right. We've talked about how these techniques could be useful in engineering and computer science.
Right.
But what other areas could benefit from this kind of research?
Oh, tons of them, potentially. We'll think about machine learning.
Cool.
Machine learning is all about optimization, right? Finding the best parameters for a model.
Right.
And the stuff we've been discussing, especially the analysis of those complexity lower bounds,
Yeah?
that could really impact how we design machine learning algorithms.
How so?
Well, it could lead to faster training times, better performance, more efficient algorithms overall.
So we could build smarter AI thanks to this research.
Exactly. And it's not just AI. Statistical physics, signal processing, economics,
Now.
all these fields could benefit anywhere you have complex systems that need optimization. These tools could be incredibly valuable.
So it's like a new way of tackling problems that were just too complex before.
That's a good way to put it.
Okay. The paper also talks about the limits of these optimization methods.
Right.
So are we hitting a ceiling? Have we reached the point where we can't improve these techniques any further?
It's important to remember that those lower bounds they found are for those specific methods.
Yeah.
So they tell us about the inherent limitations of those approaches.
Yeah.
But they don't necessarily mean that's the absolute limit for optimization in general.
So there could be ways to get around those limitations,
Exactly.
even if we've reached the limit with these specific methods.
Right. There might be entirely new optimization approaches out there, ones we haven't even thought of yet.
Okay.
Ones that could sidestep those limitations.
So there's still hope.
Oh, definitely. And we could also look at ways to modify the existing methods, maybe tailor them to work better for specific problems.
So it's more of a challenge than a dead end.
Exactly. It's about finding new creative solutions.
Yeah, I like that. So where do we go from here? What are the big open questions, the next steps for researchers?
Well, one thing that jumps out is trying to get more precise convergence bounds.
Okay.
Remember how we talked about the possibility that the actual convergence rates are faster than the upper bounds they calculated?
Yes, like that car that could go faster than 60 miles per hour.
Right. So we need to develop better tools, more refined techniques
Right.
to figure out those true convergence rates.
Okay.
Maybe we need to look at new mathematical tools or find clever ways to use the specific structure of the problem to our advantage.
So we need to get a more accurate reading, so to speak.
Exactly.
What else? What other directions could this research go?
And another exciting possibility is to see if these techniques can be applied to a broader range of problems. Right now, the focus is on minimizing polynomials on a sphere,
Right.
which is pretty specific.
Yeah.
But what about optimizing other types of functions, more complicated ones, over different sets?
Expanding the scope.
Exactly. Imagine using these techniques to optimize complex systems in biology,
Yeah. Uh-huh.
like modeling what happens inside a cell, or simulating evolution,
Right.
or designing more efficient energy grids, taking into account all the factors involved.
Okay.
We could even model social networks, how information spreads, and how communities evolve.
Sounds like the possibilities are endless.
Pretty much.
Now, I wanted to touch on the computational aspect of this.
Yeah.
It seems like these methods really rely on powerful computers to crunch the numbers.
Oh, absolutely. The Moment-sos and spectral hierarchies, they're great in theory.
Yeah.
But when you start dealing with more complex problems, the calculations can get really intense.
So there's a trade-off
Yeah.
between the accuracy of this solution and the computing power you need to find it.
Exactly. And that's why it's so important to develop more efficient algorithms.
Okay.
Maybe by exploring new computational paradigms, things like parallel computing or even quantum computing.
Quantum computer.
Yeah, that's the really cutting edge stuff.
Wow, how could that help?
Well, quantum computers have the potential to revolutionize certain kinds of calculations, especially in optimization.
I
They
see.
use quantum mechanics to their advantage,
Right.
and that could mean significantly faster solutions.
So even though there are these theoretical limits on how fast these methods can converge, the way we implement them, the computers we use, that can make a big difference.
Absolutely. It's not just about the math. It's about how math and computation intersect, how we can make these powerful tools actually work in the real world.
It's amazing to see all these different areas, math, computer science, even quantum physics, all coming together to solve these really tough problems.
It's a testament to the power of interdisciplinary research, how progress in one area can really fuel advancements in others.
Yeah. Well, I think we've covered a lot of ground in this deep dive.
We
We've
have.
explored these powerful methods, dug into those fascinating quantum theorems, and even considered the limits of computation.
It's been a great discussion. I'm really excited about all the open questions we've uncovered.
Me too.
It's clear that there's still so much to learn and discover in this field.
It's reassuring to know that even in such a complex area of math, there's always room for new ideas and new breakthroughs.
Absolutely.
It reminds us that the pursuit of knowledge is a never-ending journey.
It-
And I have a feeling that the tools and techniques we've talked about today are going to play a big role in shaping that journey, helping us find solutions to some of the most challenging problems we face.
I agree.
Well, on that note, I think it's time to wrap up our deep dive.
Sounds good.
Thanks for joining me on this intellectual adventure.
Thanks for having me.
It's been a pleasure. Until next time. Welcome to our deep dive
Yeah.
into this fascinating world of polynomial optimization on the unit sphere.
Right.
We're going to be exploring a paper called Moment-sos and Spectral Hierarchies for Polynomial Optimization on the Sphere and Quantum Definity Theorems.
Okay.
It delves into two powerful approaches for finding the minimum value of a polynomial,
Right.
the Moment-sos Approach and the Spectral Approach.
Mm-hmm.
As you know, this is a challenging problem that becomes increasingly complex.
Yeah.
beyond basic cases.
What's really intriguing is how these mathematical tools connect to quantum Finetti theorems.
Yes.
It reveals a surprising interplay between
Yeah.
seemingly unrelated areas of mathematics.
So before we dive into the specifics,
Okay.
let's set the stage.
Right.
We're dealing with the problem of minimizing a polynomial p
Yeah.
on the unit sphere,
Okay.
denoted as SN1.
Mm-hmm.
Our goal is to find Polynomial mean, the absolute minimum value of p on this sphere.
Okay.
Now, finding p indirectly can be computationally demanding.
Right.
So both the Moment-sos and spectral approaches offer ways to approximate it using cleverly constructed bounds.
The Moment-sos approach tackles this challenge by replacing the difficult non-negativity condition with a more tractable sum of squares representation.
Okay.
Imagine you're trying to check if a polynomial is non-negative everywhere on the sphere.
Okay.
That's a tough task.
Right.
Instead, the Moment-sos method looks for a way to express the polynomial as a sum of squares of other polynomials.
So rather than directly checking for non-negativity,
Right.
they're essentially asking, can we build this polynomial from squares?
Exactly.
And if the answer is yes,
Yeah.
it automatically guarantees that the original polynomial is non-negative.
Exactly. This leads to the Sassos bounds, denoted as Sassos.
Okay.
These form a sequence of increasingly accurate lower bounds for the true minimum polyn.
Okay.
As our increases,
Yeah.
the approximation gets tighter and tighter.
It's like creating a series of nested enclosures
That's a great way to put it.
around the true minimum,
Right.
getting closer with each step.
Exactly.
Computationally, you're solving a series of increasingly complex problems.
Right.
But each one gives you a better bound.
Now, on the other side,
Okay.
we have the spectral bounds,
Okay.
proposed by Lovitz and Johnston,
Right.
the authors of the paper.
Okay.
They provide a computationally less expensive alternative to the Moment-sos bounds.
And they achieve this by using doubly symmetric matrices to represent the polynomial right.
Right.
I remember from linear algebra
Yeah.
that these matrices have some special properties.
Yeah.
And you remind us how they come into play here.
Of course, doubly symmetric matrices are symmetric along both the main diagonal and the anti-diagonal.
Okay.
This symmetry allows for certain efficient eigenvalue computations, which are the heart of the spectral approach.
Right.
These eigenvalue calculations are generally faster than the semi-definite programming involved in the Moment-sos approach,
Okay.
hence the computational advantage.
Okay. So both approaches give us ways to approximate plan.
Moment-sos using sum of squares and semi-definite programming, and spectral using doubly symmetric matrices and eigenvalue computations.
Exactly.
But how do we know which one is better?
Right.
That's where the convergence analysis comes in, right?
Exactly. We want to understand how quickly these bounds approach the true minimum as we increase the order.
Okay.
This is where the paper gets really interesting as it delves into the convergence analysis of both hierarchies.
And this is where those quantum Finetti theorems enter the picture. I'm still trying to wrap my head around how those fit into all of this.
Yeah.
They seem to come from a completely different area of math.
It's a fascinating connection indeed.
Yeah.
Lovitz and Johnston, in their analysis of the spectral bounds, leveraged a quantum Finetti theorem specifically designed for complex Hermitian matrices. Their work showed that the difference between Wyman and Sparry C decreases at a rate of 0.1R.
So as you increase R, the error in the spectral bound shrinks proportionally to R.
That makes sense.
Yeah.
Now, what about the convergence of the Moment-sos bounds?
For the Moment-sos bounds, Fang and Fauci, in a separate paper, employed the polynomial kernel method to achieve an even tighter convergence rate of 0.1 or 2.
Okay.
This implies that the error in the Moment-sos bound shrinks proportionally to 1 or 2.
Okay.
Which is faster than the spectral bounds.
So Moment-sos seems to win on accuracy?
It seems so.
But it might be more computationally expensive.
Right.
That's a classic trade-off.
It is.
But the paper we're looking at digs even deeper into the connections between these two approaches, right?
Absolutely. One of the key questions they explore is whether the complex quantum Finetti theorem, which was instrumental in analyzing the spectral bounds, has a direct analog in the realm of real doubly symmetric matrices.
That's a great question.
Could a similar result be achieved?
Yeah.
Without venturing into the world of complex numbers?
Did they find such an analog? It would certainly simplify things if we could stick to real numbers.
Interestingly, their research showed that a direct, straightforward analog doesn't exist.
Oh.
They constructed a clever counterexample inspired by the work of Caves et al. On quantum de Finetti representations, proving that a simple translation from complex to real matrices doesn't work.
Okay, so a direct analog is out of the picture.
Right.
But did they manage to find any connection between real doubly symmetric matrices and these de Finetti representations?
Yes, they did. This is where their work on the banded real quantum de Finetti theorem comes in.
Okay.
It's a weaker form of the theorem,
Okay.
but it's still incredibly useful. Instead of approximating the partial trace of a real doubly symmetric matrix directly with an element of the set CDRN, as one might hope, this banded version demonstrates that it can be approximated by a scaled element of CDRN.
So it's a bit more nuanced than a direct analog.
It is.
But it still bridges the gap between real doubly symmetric matrices and these de Finetti representations. I'm guessing this banded theorem leads to a new way of analyzing the convergence of the spectral bounds.
You're exactly right.
Okay.
They use this banded theorem to rederive the O1R convergence rate for the spectral bounds, offering a fresh perspective on the original analysis by Lovitz and Johnston.
So now we have two different proofs for the same convergence rate.
Yes.
It's amazing how different mathematical tools can lead to the same destination.
I agree.
Like having multiple maps leading to the same treasure.
It's a testament to the interconnectedness of mathematics.
Right. And it's not just about finding different paths.
Right.
Sometimes these different approaches reveal insights that a single method might miss.
Exactly.
That makes a lot of sense. But the paper doesn't stop at providing an alternative proof.
No, it doesn't.
It also digs into the complexity, lower bound, for the spectral hierarchy.
Right.
Before we move on, can you remind me what a complexity lower bound is in this context?
A complexity lower bound essentially establishes the best possible convergence rate we can hope to achieve. Think of it as a speed limit for how quickly these bounds can approach the true minimum, no matter how clever our algorithms or analysis become.
That's a helpful analogy. And what did they discover about this lower bound for the spectral hierarchy?
They constructed a very specific example, a 5-variate form of degree 4 derived from the Choi-Lam form, to prove that the convergence rate of the spectral bounds can't be better than 1 error 2.
Okay.
This means no matter how we refine our methods, the error will always shrink at a rate no faster than 1 error 2.
Interesting. So although we currently have a proof for O1R convergence,
yes,
this lower bound hints that there might be room for improvement.
That's right.
Perhaps a more refined analysis could demonstrate a convergence rate closer to A1 or 2, closing that gap.
That's precisely the kind of question that keeps mathematicians up at night.
Well, this has been an incredibly insightful discussion so far.
It has.
We've covered a lot of ground.
We have.
From unpacking the Moment-sos and spectral approaches to their connection to quantum de Finetti theorems.
A lot of ground.
There's still much more to uncover.
Yes.
So let's continue our exploration in part 2 of this deep dive.
I'm looking forward to it.
Excellent. Me too.
Okay.
All right.
Great.
See you then.
Sounds good.
Bye.
Bye.
Welcome back. It's great to continue our exploration of polynomial optimization on the unit sphere.
I'm ready for more. Last time we delved into the Moment-sos and spectral approaches for approximating the minimum value of a polynomial p on the unit sphere. And we even touched upon the fascinating connection to quantum de Finetti theorems.
Exactly.
We left off with the tantalizing finding that the convergence rate of the spectral bounds can't be better than 1R2 based on a clever construction involving the Choi-Lam form.
You remember the Choi-Lam form plays a crucial role in establishing that complexity lower bound.
Right. You mentioned it's a classic example of a non-negative polynomial that can't be expressed as a sum of squares.
Exactly.
Before we dive into the details of the proof. Okay.
Can you remind me why that property of the Choi-Lam form is so important in this context?
It has to do with the relationship between sum of squares representations and the properties of certain matrices. If a polynomial can be expressed as a sum of squares, its maximally symmetric matrix representation will be positive semidefinite. Conversely, if a polynomial is non-negative but not a sum of squares, its maximally symmetric matrix representation cannot be positive semidefinite.
Ah, I see. So the fact that the Choi-Lam form is non-negative but not a sum of squares means its maximally symmetric matrix representation isn't positive semidefinite. And this is key to their proof.
Precisely. Now let's take a closer look at how they use the Choi-Lam form
Okay.
to establish the lower bound for the convergence rate of the spectral bound.
Okay, I'm all ears.
They begin with the Choi-Lam form in 4 variables denoted PCL.
Okay.
Then they introduce a clever trick.
Okay.
They add a 5th variable to artificially turn it into a 5-variate polynomial,
Okay.
which they call P-shu.
Why add a 5th variable if it doesn't really change the underlying polynomial?
It's subtle but powerful.
Okay.
The 5th variable U
Yeah.
allows them to leverage the specific properties of the spectral bounds,
Yeah.
which are defined for polynomials on the unit sphere in dimensions.
Right.
By embedding PCL into a 5-dimensional space,
Yeah.
they can analyze its behavior within the framework of the spectral hierarchy. It's like setting up the problem on a larger stage
Yeah.
so they can use the tools of the spectral approach.
That's clever.
Is
So they're essentially disguising the Choi-Lam form as a 5-variate polynomial so they can analyze it using the spectral machinery. What do they do next?
They define stairs as the sum of squares of all 5 variables.
Okay.
U2 plus by 12, plus by 22, plus by 32, plus by 42.
Hmm.
This will play a role in constructing the matrices needed for the spectral bound.
Okay. And then they define Q and M as the
Yes.
maximally symmetric matrices representing P and S2 respectively, right?
Exactly. And they use these matrices to construct the spectral bound of order, or denoted spare. Remember, the goal is to show that spare,
Yeah.
which is a lower bound for the true minimum p-bin,
Right.
cannot converge to p-bin any faster than 1 or 2.
Right. So we need to analyze how spread behaves as increases. How do they approach that?
Their proof hinges on analyzing a specific principal submatrix H
Okay.
of a larger matrix here.
Okay.
This G is derived from Q and M
Okay.
and incorporates the spectral bound spare.
Why focus on this particular submatrix H? What's so special about it?
They cleverly choose H so that it captures essential information about the behavior of the spectral bounds
Okay.
to understand why we need to look at how H is constructed.
Okay, let's get into the details.
The entries of H are determined by carefully counting how many permutations of the indices contribute to each element.
Okay.
This involves considering the structure of the matrices Q and M
Right.
and how they relate to the polynomial P and the sum of squares S2. It's a bit intricate, but the key takeaway is that the entries of H reflect the way the spectral bound spar is constructed.
So they're essentially using combinatorics to extract information about spar from the structure of these matrices.
That's a good way to put it.
It's amazing how different areas of math come together in this proof.
It really is. It's a beautiful example of how mathematical tools from different fields can complement each other.
Yeah. Now, the next step involves showing that H can be expressed in a particular form.
Right.
What form is that?
They show that H can be written in terms of the maximally symmetric representation of PCL in 4 variables.
Okay.
Remember, that's the original Choi-Lam form,
Right.
along with the projection matrix onto the symmetric subspace of 4 variate polynomials
Oh.
and a scaling factor involving spar.
Wow. It's like they've distilled all the essential information about the problem into this one matrix H. What do they do with this representation of H?
This is where it all comes together. They use the fact that H at a
Jeez.
principal submatrix of GER must be positive semidefinite.
Why is that?
Because GRE itself is constructed in a way that guarantees it's positive semidefinite.
Right.
And any principal submatrix of a positive semidefinite matrix is also positive semidefinite.
Right.
It's a fundamental property of such matrices.
So they leverage the positive semi-definiteness of H to
Yeah.
get information about string.
Precisely. Combining the positive semi-definiteness of H with the properties of the projection matrix
Right.
and the maximally symmetric representation of H2,
Okay.
they derive a lower bound on spring.
And what is that lower bound?
The lower bound they obtain is proportional to 100 hour 2. This is the crucial result.
Okay.
It proves that the convergence rate of the spectral bounds cannot be any better than 1 error 2.
That's a remarkable achievement. They've used a clever combination of linear algebra,
They have?
combinatorics, and properties of the Choi-Lam form to establish a fundamental limit
Yes.
on how quickly these spectral bounds can converge.
It's a testament to the power of mathematical reasoning. And this result about the Choi-Lam form extends to a broader conclusion about the banded real quantum de Finetti theorem we discussed earlier.
I'm all for broader conclusions. Tell me more.
They use the Choi-Lam example to demonstrate that there exists a unit vector v for which the approximation error in the banded real quantum de Finetti theorem can't be better than 1R2. This means the convergence rate in that theorem is inherently limited by this 1R2 factor.
So while the banded theorem provides a way to approximate real doubly symmetric matrices using scaled elements of CDRN, this example shows that the approximation can be arbitrarily good.
That's right.
There's a fundamental limit to its accuracy. And it's tied to this 1R2 factor that popped up in our analysis of the Choi-Lam form.
Precisely. The Choi-Lam form serves as a concrete example that eliminates a fundamental limitation inherent in the banded real quantum de Finetti theorem. These concepts are deeply intertwined.
This is all fascinating, but I have to admit my brain is starting to feel a bit overloaded.
I understand.
Before we move on, I think it would be helpful to take a step back and try to connect what we've been discussing to a broader mathematical concept you mentioned earlier, the moment problem.
Yes. The moment problem is a fascinating area of mathematics that asks, given a sequence of numbers, can we construct a measure whose moments match those numbers?
Can you unpack that a bit? What do you mean by moments in this context?
In probability theory, the moments of a probability distribution provide information about its shape and characteristics. For example, the first moment is the mean. The second moment relates to the variance and so on. The moment problem is like a reverse engineering puzzle. We're given the answers, the moments, and we're trying to figure out the question, the measure.
So it's like we're trying to reconstruct a hidden probability distribution from a set of clues. And how does this connect to our discussion about polynomial optimization and de Finetti theorems?
Think of it this way. In the Moment-sos approach, we're essentially searching for a measure supported on the unit sphere whose moments match the coefficients of the polynomial we're trying to minimize. If we can find such a measure, its support, the points where it has non-zero probability will tell us where the polynomial achieves its minimum value.
So the moment problem is like the underlying puzzle.
It is.
And these techniques we've been discussing are different ways of solving it.
That's right.
Or at least getting closer to a solution.
Exactly.
We're using these sophisticated tools to find the hidden measure that corresponds to the polynomial we're trying to minimize.
That's a fantastic analogy. And the real de Finetti theorems we've been discussing provide tools for tackling a specific type of moment problem. One where the measures are supported on the sphere and have a particular symmetry property.
So instead of trying to find a measure that perfectly matches all the moments, these theorems offer a way to approximate them. Providing a measure whose low-degree moments are close to the target moments.
And the error bounds we've been discussing, like O1R2 for the real quantum de Finetti theorem for maximally symmetric matrices, and O1R for the banded real quantum de Finetti theorem. Quantify how good those approximations can be.
This is all starting to click into place. These de Finetti theorems are powerful tools for tackling specialized moment problems.
They are.
Which in turn helps us analyze the convergence of these optimization hierarchies. We're using the language of probability and measures to understand the behavior of polynomials on the unit sphere.
Precisely. It's a beautiful example of how seemingly disparate areas of mathematics can be deeply interconnected.
And this connection is not just a theoretical curiosity. It has practical implications for fields like machine learning and quantum computing. I'm really curious about those applications. I know we've covered a lot of ground already.
We have.
But I think my brain is ready for a little more.
I agree. Let's delve into those applications next.
Welcome back to our deep dive into the world of polynomial optimization.
It's been quite a journey.
We've been on quite a journey exploring the Moment-sos and spectral approaches, their connections to quantum de Finetti theorems, and even the surprising link to the moment problem. It's amazing how these seemingly abstract concepts are all intertwined.
It's a testament to the elegance and interconnectedness of mathematics.
Absolutely. And as promised, let's shift gears a bit and explore how these theoretical tools can be applied to real-world problems in fields like machine learning and quantum computing. I'm particularly interested in the machine learning applications. Can you give us some concrete examples of how polynomial optimization techniques are used in that field?
Certainly. At its core, machine learning often boils down to optimizing complex functions. For instance, when you're training a neural network, you're essentially searching for the best set of parameters that minimize some error function.
Okay.
And in many cases, these error functions can be represented as polynomials.
So instead of trying to minimize an arbitrary function,
Right.
which could be very messy,
It can
you can often translate the problem into minimizing a polynomial.
Exactly.
And that's where these techniques we've been discussing come in handy.
Precisely. The Moment-sos and spectral hierarchies provide systematic and powerful ways to approximate the solutions to these polynomial optimization problems.
Okay.
They offer a valuable balance between accuracy and computational efficiency,
Right.
which is crucial in machine learning, where data sets can be massive.
But what about quantum computing?
Okay.
Earlier, you mentioned that quantum to Finetti theorems play a role in understanding quantum states.
They do.
Especially those involving entanglement.
Right.
Can you elaborate on that?
Quantum to Finetti theorems are essential tools for characterizing and analyzing quantum states,
Okay.
particularly those involving multiple entangled particles.
Okay.
They provide a way to understand the structure and properties of these states, which are the building blocks of quantum computation.
So these theorems help us make sense of the complex world of entangled particles,
They do.
which are notoriously difficult to grasp intuitively.
Right.
But how do these theorems connect to the polynomial optimization techniques we've been discussing?
The polynomial optimization techniques we've explored, particularly those based on the Moment-sos and spectral hierarchies, can be used to analyze and manipulate these quantum states.
Okay.
For example, they can help us understand the limitations of certain quantum algorithms,
Okay.
or design new, more efficient algorithms for specific computational tasks.
It sounds like these polynomial optimization techniques are becoming indispensable tools
They are.
for researchers working at the forefront of quantum computing.
Absolutely. They provide a powerful mathematical framework for tackling some of the most challenging problems in this rapidly developing field.
It's remarkable how these seemingly disparate areas of mathematics,
That is.
polynomial optimization, quantum to Finetti theorems, and even the moment problem,
It is.
have converged to provide such a rich and powerful set of tools.
Right.
It makes you wonder what other surprising connections are waiting to be discovered.
I completely agree. It's this constant interplay between exploration, discovery, and connection that makes mathematics so fascinating and endlessly rewarding.
Speaking of discoveries, the paper we've been discussing mentions some open questions
It does.
that are still actively being researched.
Right.
Can you highlight a few that you find particularly intriguing?
One that stands out is the question of whether the gap between the lower bound 1R2 and the upper bound O1R for the spectral bounds can be closed.
Okay.
Can we find a more refined analysis? That demonstrates that the spectral bounds actually converge at a rate closer to 1R2.
If that were possible, it would be a significant result.
It would be.
It would mean that the spectral approach, despite its computational advantages, could potentially achieve accuracy comparable to the more computationally demanding Moment-sos method.
Yes.
That would have major implications
It would.
for both machine learning and quantum computing.
Indeed. Another compelling open question is whether we can develop even faster algorithms for solving these polynomial optimization problems. As we tackle more complex problems in machine learning, quantum computing, and other fields, we'll need increasingly efficient algorithms to keep pace.
It's like an ongoing race between the complexity of the problems we're trying to solve
It is.
and the ingenuity of the mathematical tools we develop to solve them.
I love that analogy. And it's this constant interplay between challenges and innovations that drives progress in mathematics and its applications.
Well, this has been an incredibly insightful and thought-provoking deep dive.
It has.
We've covered a remarkable amount of ground.
We have.
From the intricacies of mathematical proofs to the potential for real-world impact in fields like machine learning and quantum computing.
A lot of ground.
It's clear that the world of polynomial optimization is far from exhausted.
Far from it.
It's a vibrant field with many exciting avenues for future research.
I couldn't agree more. And to our listeners, I encourage you to delve deeper into the areas that pique your interest.
Yes.
Perhaps this exploration has sparked new questions or connections in your own minds. After all, that's the beauty of mathematics. It's a journey of endless discovery.
Beautifully said. And on that note of endless possibilities, I think it's time to wrap up our deep dive.
Okay.
Thank you for joining us on this fascinating exploration. Until next time, keep those mathematical minds engaged and never stop diving deep.
Great talking to you.
Likewise. Thanks for joining us.
Bye-bye.
Welcome to the deep dive, where we take these complex topics and kind of break them down, in a way that's both informative and engaging.
Mm-hmm.
Today we're diving into the world of polynomial optimization on the unit sphere.
Okay.
Which is, it's a really fascinating area of research.
Yeah.
It's got connections to fields like quantum information theory and theoretical computer science.
It really is. It's a surprisingly versatile problem. Lots of interesting applications.
Now, I know you're no stranger to the world of mathematics.
Right.
So we're gonna skip the basic introductions and get right into it.
Sounds good.
So we'll be looking at this research paper called Moment-sos and Spectral Hierarchies for polynomial optimization on the sphere and quantum to Finetti theorems.
Wow.
It's a mouthful.
Yeah.
But it explores the convergence analysis of two powerful approximation hierarchies used to solve these types of problems.
Right. We'll be exploring the Moment-sos hierarchy, which gives us semi-definite bounds, and the spectral hierarchy, which yields spectral bounds.
And what makes this paper particularly interesting is its use of quantum to Finetti theorems.
Right.
Which were, they were initially developed for quantum information theory.
Yeah.
But now they're proving to be incredibly useful in the field of optimization.
That's right.
So are you ready to dive in?
Absolutely.
Let's get started.
Let's go.
Okay, so let's start by clearly defining the problem. We're interested in minimizing a polynomial, we'll call it P, over the unit sphere in n dimensions.
Okay.
This can be mathematically expressed as minimizing px, where x belongs to Rn, and the norm of x, denoted as x02, equals 1.
So essentially, we're trying to find the lowest point on a surface, defined by a polynomial, but restricted to the points that lie on the unit sphere.
Exactly. And as you mentioned earlier, this problem has implications in various fields. Can you elaborate on that a bit?
Sure. So in quantum information theory, this problem is relevant to understanding the entanglement and separability of quantum states.
Okay.
Entanglement is this really fascinating phenomenon where quantum particles become linked in a way that their fates are intertwined even when separated by large distances.
Wow.
By minimizing certain polynomials over the unit sphere, we can gain insights into the nature and properties of entangled states.
That's amazing. It's always fascinating to see how these seemingly abstract mathematical concepts can have such profound implications in other fields.
Right.
Yeah.
And it doesn't stop there. This problem also has applications in modeling matrix norms, which are crucial in various areas of mathematics and computer science.
Okay, I'm convinced this is a problem we're solving. So how do these approximation hierarchies, the Moment-sos and the spectral, come into play?
Well, these hierarchies provide systematic ways to approximate the minimum value of the polynomial on the sphere.
Okay.
They work by constructing a sequence of increasingly accurate lower bounds, meaning that we can get as close to the true minimum as we want by going far enough in the hierarchy.
So it's like building a staircase that gets closer and closer to the true minimum value, like with each step.
Yeah, that's a great analogy.
Okay.
Let's start by delving into the Moment-sos hierarchy.
Okay.
Which relies on the concept of sum of squares polynomials.
Okay, I'm familiar with sum of squares polynomials, but for our listeners who might not be, can you give us a quick refresher?
Of course. A polynomial is said to be a sum of squares, or SOS, if it can be written as the sum of squares of other polynomials. For example, the polynomial by 2 plus 2 by psi plus y2 is an SOS because it can be written as x plus y2.
Right. And the key idea here is that any SOS polynomial is always non-negative.
Exactly. And that property is crucial for the Moment-sos hierarchy.
Okay.
It uses these SOS polynomials to construct lower bounds for the minimum value of our polynomial p.
So how does it work in practice? Can you walk us through the steps involved in constructing these bounds?
Certainly. The Moment-sos hierarchy is based on a sequence of optimization problems called semidefinite programs, or SDPs.
Right.
These SDPs are a generalization of linear programs and allow us to optimize over the cone of positive semidefinite matrices.
I'm familiar with SDPs, but I'm curious how how they're used specifically to construct the SOS bounds for our problem.
So at each level of the hierarchy,
Okay.
we solve an SDP to find the largest value of L such that the polynomial Px
Okay.
can be expressed as an SOS polynomial
Right.
plus a term that vanishes on the unit sphere.
So we're essentially trying to find the largest constant we can subtract from our polynomial.
Yes.
While still ensuring that the result can be written as a sum of squares plus a term that disappears on the sphere.
Precisely.
Okay.
And this largest value of L becomes our lower bound at level R.
Got it.
Denoted as so's were, mathematically we can express this as so bir. Mathematically we can express this as max low OR plus U1 opal 22, where is an SOS polynomial and U is another polynomial, both having degrees less than or equal to 2R.
That's a very concise way of expressing the idea.
Right.
I'm curious about the convergence rate of these bounds.
Okay.
As we increase the level R, how quickly do these bounds approach the true minimum of the polynomial?
That's a key question, and one that has attracted a lot of attention from researchers.
Right.
Earlier work by Resnick, Doherty, and Wiener established a convergence rate of O1R.
Okay.
Meaning that the error between the bound and the true minimum decreases proportionally to 1.
So as we go higher in the hierarchy, the error shrinks.
Yes.
But at a rate proportional to 1R.
That's right.
But I understand there have been improvements on this rate, right?
Yes. Fang and Fauzi made a significant contribution by proving a faster convergence rate of O1R2.
That's quite a speed up.
Yeah.
How did they manage to achieve this improvement?
Their approach cleverly uses the polynomial kernel method. They construct a specific kernel function, which allows them to build a more efficient representation of the polynomial. This leads to a tighter bound and ultimately a faster convergence rate.
So by using like a carefully chosen kernel, they were able to exploit the structure of the problem more effectively, leading to a better result.
That's a great summary.
Okay.
So that covers the Moment-sos hierarchy,
right,
which uses semi-definite programming to generate lower bounds for our optimization problem.
Right. Now let's move on to the spectral hierarchy.
Okay.
Which, as you mentioned earlier, takes a different approach using eigenvalue computations.
Exactly. The spectral hierarchy was introduced by Lovitz and Johnston.
Okay.
And it leverages the properties of specific matrices constructed from the polynomial to obtain the bounds.
I'm intrigued.
Yeah.
Can you elaborate on how these matrices are constructed?
Yeah.
And how their eigenvalues relate to the minimum value of the polynomial?
Of course. The key idea behind the spectral hierarchy is to construct a sequence of matrices called doubly symmetric matrices.
Okay.
These matrices are derived from specific sum of squares representations of the polynomial on the sphere.
Okay. But before we go further, can we pause for a second and talk about these doubly symmetric matrices?
Sure.
I'm not sure I fully grasp what that term means.
You're right. It's a concept that might need a little clarification. Imagine a matrix.
Okay.
Now imagine shuffling its rows.
Okay.
And if you get the same matrix back, it's symmetric.
Okay. Yeah.
Now do the same thing for columns. If the matrix remains unchanged after shuffling both rows and columns, then it's called doubly symmetric.
I see. So it has this property of being symmetric along both dimensions.
Exactly.
Got it.
And the spectral hierarchy exploits the specific structure of doubly symmetric matrices to obtain bounds for the minimum value of the polynomial. The spectral bound at level R, denoted as spray, is defined as the smallest eigenvalue of a particular matrix constructed from the polynomial in the level R. This matrix is essentially a representation of the polynomial in a higher dimensional space where the doubly symmetric structure becomes apparent.
So by moving to this higher dimensional representation, we can leverage the doubly symmetric structure to extract information about the minimum value.
Precisely. And one of the advantages of the spectral hierarchy is that computing eigenvalues is generally faster and less resource intensive than solving semi-definite programs, which are used in the Moment-sos hierarchy.
So in terms of computational efficiency, the spectral hierarchy has a potential edge.
Yes, especially for large-scale problems where computational cost becomes a significant factor.
Okay, so we've got these two powerful hierarchies, each with its own strengths and weaknesses.
Right.
But here's where I'm really curious. You mentioned earlier that this research connects these hierarchies to quantum Finetti theorems.
Yes.
Now that sounds fascinating. Can you shed some light on this connection and how it comes into play?
That's where things get really interesting.
Okay.
The connection might seem surprising at first,
Yeah.
but it turns out that these theorems from quantum information theory can be incredibly useful for analyzing the convergence rates of these optimization hierarchies.
I'm all ears. Explain it to me like I'm 5.
Okay. Imagine you have a complex quantum system
Okay.
with many entangled particles.
Ah.
These particles are interacting in a way that's hard to describe exactly.
Okay.
What a de Finetti theorem does is it allows you to approximate this complex entangled state by a much simpler one where the particles are considered independent.
So it's like taking a tangled mess of strings and finding a way to approximate it by a bunch of neatly separated strings.
That's a good analogy.
Okay.
And the simplification is incredibly useful because it makes the system much easier to analyze. Now, in the context of polynomial optimization, the quantum de Finetti theorem helps us approximate certain matrices that arise in the analysis of the spectral hierarchy by simpler ones that are easier to handle.
So even though we're dealing with classical optimization problems,
Yes.
we can borrow tools from quantum information theory to simplify our analysis.
Exactly. And that's the beauty of mathematics. Often, tools developed in one area find unexpected and powerful applications in seemingly unrelated fields.
It's amazing how these connections emerge.
It is.
So these quantum de Finetti theorems are like these mathematical bridges connecting the world of quantum states with the world of polynomial optimization.
Exactly. And Lovitz and Johnston specifically use one of these theorems to prove a convergence rate of O1R for their spectral hierarchy.
Which, at that time, was on par with the Moment-sos hierarchy.
Yes. But there's a slight twist. The quantum de Finetti theorem they use is designed for complex Hermitian matrices.
But our original problem deals with real numbers.
Right.
And real valued polynomials. So how do they bridge that gap?
They cleverly connect the real optimization problem to its complex counterpart.
Okay.
And manage to utilize this complex quantum de Finetti theorem to analyze the spectral bounds, even though our problem is inherently over real numbers.
That's impressive. So they essentially found a way to use a complex tool to solve a real problem.
Yes, and it worked beautifully. But it does raise a question.
Yeah.
Wouldn't it be more natural to have a de Finetti theorem specifically tailored for real matrices?
Right.
After all, our optimization problem is in the realm of real numbers.
That's a great point. It seems like a more direct approach. So is there such a theorem for real matrices?
That's what we investigated as well.
Okay.
And it turns out that extending the quantum de Finetti theorem to real doubly symmetric matrices is trickier than it might appear.
Really?
In fact, a direct real analog doesn't quite work.
Oh, how so? What's the obstacle?
There's a concrete counterexample inspired by the work of Caves et al. That demonstrates why a direct real analog fails. This counterexample essentially shows that you can't always approximate a real doubly symmetric matrix by a convex combination of rank 1 matrices based on real unit vectors with the same accuracy as in the complex case.
So direct translation of the theorem from the complex world to the real world doesn't work.
Exactly. But don't despair.
Okay.
While a perfect real analog doesn't exist,
Yeah.
we can still salvage something. We introduce a banded real de Finetti theorem for doubly symmetric matrices.
Banded, okay.
This theorem offers a weaker approximation guarantee, but it's still powerful enough to allow us to analyze the spectral bounds directly in the real domain.
Banded. That sounds intriguing. What does that mean in this context?
Instead of approximating the partial trace directly as in the original quantum de Finetti theorem,
Okay.
this banded version approximates a slightly modified version, a banded version, that involves a scalar and an element from the set CDE. This set consists of convex combinations of rank 1 matrices built from real unit vectors.
So we're essentially adding a little tweak to make things work in the real domain.
Precisely.
Okay.
And while it's weaker, it still allows us to work directly with real matrices without having to resort to the complex world.
So what's the trade-off for this weaker version?
Yeah.
Does it affect the convergence rate?
That's a key question. Let's see how this banded theorem affects our analysis of the spectral hierarchy. Remember, we're aiming to minimize a polynomial p on the unit sphere using the hierarchy of spectral bounds denoted as SPR.
Right. These bounds give us increasingly accurate estimates of the true minimum as we go higher in the hierarchy.
Exactly. Now, Lovitz and Johnston originally used the complex quantum de Finetti theorem to prove a convergence rate of O1R for these bounds.
Right.
We're going to follow a different path and use our banded real de Finetti theorem to achieve the same rate, but directly in the real domain.
Okay, sounds good. Lead the way.
All right, let's start by recapping some key definitions. We have Q, which is the maximally symmetric matrix representation of our polynomial P.
Okay.
And then there's M, the maximally symmetric matrix representation of S, where S is the sum of squares of our variables, and D is the degree of the polynomial. Finally, we have Cure and Mr, which are doubly symmetric matrices representing ISR and S respectively.
Okay, these matrices are like the building blocks of our spectral hierarchy.
Now, the heart of our analysis hinges on a clever identity.
Okay.
This identity relates the matrices we just defined and states that the inner product of core Mr with the outer product of a unit vector V with itself is equal to 0. This identity holds because V is an optimal solution to the program that defines the spectral bound.
So we're essentially using the optimality condition of V to establish a relationship between these matrices.
Exactly.
Okay.
And this relationship is crucial. Using this identity and some properties of partial traces and maximal symmetrization, we can express the difference between the true minimum P line and our spectral bound as an inner product involving the matrix tupli and a specially chosen matrix from our set CDRN.
Okay, so we've connected the error, that's PPNan, to these matrices and a particular element from CDRN.
Now here's where our banded real de Finetti theorem comes into play.
Okay.
It guarantees the existence of this CDRI that allow us to control the approximation error. This theorem is crucial because it ensures that we can find a suitable that's close enough to a scaled version of the maximally symmetrized partial trace of VBT, the outer product of our unit vector phi.
So the banded theorem is like a safety net, ensuring we can find a good approximation.
Precisely. By applying this theorem, along with Holder's inequality and some careful bounding of matrix norms, we can finally demonstrate that the error prime is upper bounded by a term that decreases proportionally to 1R.
And that, my friend, gives us the coveted O1R convergence rate for the spectral hierarchy, achieved directly in the real domain.
Exactly. It highlights the power of working with real-value tools and cleverly leveraging the problem structure to achieve our goal.
Okay, we've successfully analyzed the spectral hierarchy using the banded real de Finetti theorem, but I'm always curious to know if we can push the limits even further.
Yeah.
Could there be a faster convergence rate hiding somewhere? Could we achieve something like O1R2 for the spectral hierarchy, like Fang and Fauzi did for the Moment-sos hierarchy?
That's an excellent question. It's natural to wonder if we can squeeze out even better performance.
So is there a possibility of a hidden speed boost for the spectral hierarchy?
Well, prepare for a bit of a reality check. We're about to demonstrate that the convergence rate for the spectral hierarchy cannot be better than O1R2. This means that O1R is essentially the best we can achieve.
Oh, I love these moments when we uncover these inherent limitations.
Yeah.
It's like mapping the boundaries of what's mathematically possible.
Absolutely. And the key to proving this lower bound lies in a clever construction based on the Choi-Lam form.
Okay.
Now, this form is a bit of a celebrity in the world of polynomials. It's a non-negative polynomial that refuses to be written as a sum of squares.
Wait a minute. I thought all non-negative polynomials could be expressed as sums of squares.
Right.
Isn't that like the foundation of SOS methods?
That's a common misconception. While it's true for many cases, the Choi-Lam form is a classic counterexample. It's a non-negative polynomial that simply cannot be represented as a sum of squares.
So it's a rebel in the polynomial world.
Exactly.
No.
And we're going to use this rebel to construct a specific 5-variable polynomial, which we'll also call P.
Okay.
This polynomial is essentially the Choi-Lam form in disguise, viewed as a 5-variable polynomial with an additional variable u that doesn't actually appear in the expression.
So it's like we're introducing a phantom variable.
Precisely. The reason for this trickery will become clear soon.
Okay.
The important point is that the maximally symmetric matrix representation of this 5-variable polynomial, denoted as Q, will inherit the non-sum of squares nature of the Choi-Lam form.
Okay.
It will have a block structure with a 0 block corresponding to our phantom variable.
Okay, so we've constructed this special polynomial and its matrix representation.
Right.
How do we use it to prove the lower bound?
We're going to focus on a specific principal submatrix of the matrix GR.
Okay.
This GR matrix appears in the definition of the spectral bound, but shifted by a term involving the absolute value of the spectral bound multiplied by the matrix mixture. We'll call this submatrix H.
So we're zooming in on a specific part of G
Yes.
and analyzing its properties.
Exactly. And the choice of this submatrix is strategic.
Okay.
By carefully examining the structure of H and using the properties of the Choi-Lam form, we can show that it can be expressed as the sum of two matrices.
Okay.
One involves the maximally symmetric matrix representation of the original Choi-Lam form, and the other involves the projection matrix onto the symmetric subspace of four variable polynomials.
Okay. We've expressed H as the sum of two special matrices.
Right.
What's the next step?
The magic happens when we exploit the fact that H must be positive semidefinite.
Okay.
Using this property, along with some inequalities involving the matrix M, we can derive a lower bound on the absolute value of the spectral bound.
And what does this lower bound tell us?
It reveals that the spectral bound cannot decrease faster than 1R2.
Okay.
In other words, the convergence rate of the spectral hierarchy is lower bounded by a 1R2.
So we've hit a fundamental limit.
Yeah.
No matter how much we try, we can't get a convergence rate better than O1R2 for the spectral hierarchy.
Right.
The Choi-Lam form really set a boundary here.
Exactly. It's a beautiful example of how a seemingly abstract mathematical concept can have profound consequences for the performance of optimization algorithms.
So we've established the best possible convergence rate for the spectral hierarchy.
Yes.
But what about the banded real de Finetti theorem?
Right.
Does this lower bound for the spectral hierarchy imply anything about the limitations of the banded theorem?
It does. Remember, we use the banded real de Finetti theorem to analyze the spectral hierarchy.
Right.
So our lower bound for the spectral hierarchy implies a corresponding lower bound for the approximation error in the banded real de Finetti theorem.
Okay.
Essentially, we can construct a specific unit vector for which the approximation error in the banded theorem is also lower bounded by my1R2.
So the banded theorem also has a fundamental limit in its approximation capability.
Precisely. We can't expect to achieve an arbitrarily fast convergence rate when approximating real doubly symmetric matrices using this theorem.
It seems like these lower bounds are highlighting the inherent challenges of working with real valued objects in this context.
You're absolutely right. These lower bounds aren't just abstract mathematical curiosities.
Right.
They provide valuable insights into the limitations of our tools and help us set realistic expectations for performance.
Okay, we've covered a lot of ground. We've explored the convergence analysis of the spectral hierarchy, proved a fundamental lower bound, and even uncovered implications for the banded real de Finetti theorem. What a journey.
It is.
But before we move on to the final part of our discussion, I'm curious about the bigger picture. We've seen this fascinating interplay between polynomial optimization and quantum information theory.
Right.
Is this just a coincidence?
Yeah.
Or is there something deeper at play?
It's more than a coincidence, I believe. Both polynomial optimization and quantum information theory are fundamentally concerned with representing and manipulating complex systems. In polynomial optimization, we're trying to find the optimal value of a function, often under various constraints.
And in quantum information theory, we're dealing with the complexities of quantum states, entanglement, and all the fascinating phenomena that arise in the quantum world.
Exactly. Yet, the mathematical tools developed in one field often prove surprisingly useful in the other. For instance, the idea of representing a polynomial as a sum of squares has deep connections to the concept of representing a quantum state as a density matrix. These seemingly different concepts share a common mathematical structure.
It's like discovering a hidden passageway connecting different realms of mathematics.
Precisely. And the quantum de Finetti theorems are a prime example of this cross-pollination. They were initially developed for handling the complexities of quantum states, but now we're finding they have remarkable applications in analyzing classical optimization algorithms.
So this connection is more than just a fleeting similarity.
Yeah.
It suggests a deeper mathematical unity underlying these fields.
Absolutely. And as we continue exploring these areas, we're likely to uncover even more surprising connections and powerful tools that bridge the gap between the classical and the quantum.
This has been an incredible journey. But like any good adventure, it has to come to an end. Before we wrap up, though, I'd love to hear about some of the open questions and future directions that you're most excited about.
There are so many intriguing avenues to explore, but let's start with the banded real de Finetti theorem. We know its convergence rate is lower bounded by 1 or 2,
Right.
and we have an upper bound of O and R.
Okay.
But the exact convergence rate remains a mystery.
So there's still a gap in our understanding.
Exactly. And closing that gap would be significant. It would give us a more precise understanding of the approximation capabilities of this theorem and its implications for analyzing real valued optimization problems.
What about the Moment-sos hierarchy?
Right.
We discussed the impressive O1R2 convergence rate achieved by Fang and Fauci.
Right.
But is that the best possible rate?
That's another exciting open question. We currently only have an upper bound. It's possible that the Moment-sos hierarchy has a hidden speed boost that we haven't yet discovered. Proving a tight lower bound for this hierarchy would be a major breakthrough.
It's like we're wondering if there's a turbo button on the Moment-sos engine.
Precisely. And finding that button would be a game changer.
As we conclude this deep dive, I want to encourage our listeners to continue exploring this fascinating area.
Yes.
The full paper, Moment-sos and Spectral Hierarchies for Polynomial Optimization on the Sphere and Quantum de Finetti Theorems, is available online. It's a treasure trove of insights, and I highly recommend diving in.
And remember, this is an active area of research.
Yes.
There are still many unanswered questions and uncharted territories to explore. Who knows, maybe one of our listeners will be the one to make the next big breakthrough.
On that note, we've reached the end of our deep dive. Thank you for joining us on this incredible journey through the world of polynomial optimization and quantum information theory.
It's been a pleasure sharing our insights with you. Keep those thinking caps on and never stop exploring the fascinating world of mathematics.
Until next time, may your mathematical adventures be filled with wonder and discovery. Okay, so quantum de Finetti theorems are like these, these mathematical bridges connecting the world of quantum states with the world of polynomial optimization.
Exactly. And Lovitz and Johnston specifically use one of these theorems to prove a convergence rate of O1R for their spectral hierarchy.
Which at that time was like on par with the Moment-sos hierarchy.
Yes, but there's a slight twist. The quantum de Finetti theorem they use is designed for complex Hermitian matrices.
But our original problem deals with real numbers and real valued polynomials. So how did they bridge that gap?
They cleverly connect the real optimization problem to its complex counterpart and manage to utilize this complex quantum de Finetti theorem to analyze the spectral bounds, even though our problem is inherently over real numbers.
It's impressive. So they essentially found a way to use a complex tool to solve a real problem.
Yes, and it worked beautifully. But it does raise a question. Wouldn't it be more natural to have a de Finetti theorem specifically tailored for real matrices? Right. After all, our optimization problem is in the realm of real numbers.
That's a great point. It seems like a more direct approach.
Yeah.
So is there such a theorem for real matrices?
That's what we investigated as well. And it turns out that extending the quantum de Finetti theorem to real doubly symmetric matrices is trickier than it might appear. In fact, a direct real analog doesn't quite work.
Oh, how so? What's the obstacle?
There's a concrete counterexample inspired by the work of Caves et al. That demonstrates why a direct real analog fails. This counterexample essentially shows that you can't always approximate a real doubly symmetric matrix by a convex combination of rank 1 matrices based on real unit vectors with the same accuracy as in the complex case.
So the direct translation of the theorem from the complex world to the real world doesn't work.
Exactly, but don't despair. While a perfect real analog doesn't exist, we can still salvage something. We introduce a banded real de Finetti theorem for doubly symmetric matrices. This theorem offers a weaker approximation guarantee, but it's still powerful enough to allow us to analyze the spectral bounds directly in the real domain.
Banded. That sounds intriguing. What does that mean in this context?
Instead of approximating the partial trace directly, as in the original quantum de Finetti theorem, this banded version approximates a slightly modified version, a banded version that involves a scalar and an element from the set CDRn. This set consists of convex combinations of rank 1 matrices built from real unit vectors.
So we're essentially adding a little tweak to make things work in the real domain.
Precisely. And while it's weaker, it still allows us to work directly with real matrices without having to resort to the complex world.
So what's the trade-off for this weaker version? Does it affect the convergence rate?
That's a key question. Let's see how this banded theorem affects our analysis of the spectral hierarchy. Remember, we're aiming to minimize a polynomial p on the unit sphere using the hierarchy of spectral bounds denoted as
Right. These bounds give us increasingly accurate estimates of the true minimum as we go higher in the hierarchy.
Exactly. Now, Lovitz and Johnston originally used the complex quantum Finetti theorem to prove a convergence rate of O1R for these bounds. We're going to follow a different path and use our banded real Finetti theorem to achieve the same rate, but directly in the real domain.
Okay, sounds good. Lead the way.
All right. Let's start by recapping some key definitions. We have Q diffel P, which is the maximally symmetric matrix representation of our polynomial P. And then there's M, the maximally symmetric matrix representation of S, where S is the sum of squares of our variables, and D is the degree of the polynomial. Finally, we have QRP and Mr. N, which are doubly symmetric matrices representing Arstavino respectively.
Okay, these matrices are like the building blocks of our spectral hierarchy.
Now, the heart of our analysis hinges on a clever identity. This identity relates the matrices we just defined and states that the inner product of, with the outer product of a unit vector with itself is equal to 0. This identity holds because V is an optimal solution to the program that defines the spectral bound.
So we're essentially using the optimality condition of V to establish a relationship between these matrices.
Exactly, and this relationship is crucial. Using this identity and some properties of partial traces and maximal symmetrization, we can express the difference between the true minimum atom and our spectral bound as an inner product involving the matrix Q pi E atom and a specially chosen matrix from our set CDRN.
Okay, so we've connected the error, that's pi mins, to these matrices, and a particular element from CDRN.
Now, here's where our banded real Finetti theorem comes into play. It guarantees the existence of this niglia that allow us to control the approximation error. This theorem is crucial because it ensures that we can find a suitable EAT that's close enough to a scaled version of the maximally symmetrized partial trace of VVT, the outer product of our unit vector V.
So the banded theorem is like a safety net, ensuring we can find a good approximation.
Precisely. By applying this theorem along with Holder's inequality and some careful bounding of matrix norms, we can finally demonstrate that the error is upper bounded by a term that decreases proportionally to 1 free.
And that, my friend, gives us the coveted convergence rate for the spectral hierarchy achieved directly in the real domain.
Exactly. It highlights the power of working with real-valued tools and cleverly leveraging the problem structure to achieve our goal.
Okay, we successfully analyzed the spectral hierarchy using the banded real Finetti theorem. But I'm always curious to know if we can push the limits even further. Could there be a faster convergence rate hiding somewhere? Could we achieve something like O1R2 for the spectral hierarchy, as Fang and Fauci did for the Moment-sos hierarchy?
That's an excellent question. It's natural to wonder if we can squeeze out even better performance.
So, is there a possibility of a hidden speed boost for the spectral hierarchy?
We'll prepare for a bit of a reality check. We're about to demonstrate that the convergence rate for the spectral hierarchy cannot be better than O1R2. This means that O1R is essentially the best we can achieve.
Oh, I love these moments when we uncover the inherent limitations. It's like mapping the boundaries of what's mathematically possible.
Absolutely. And the key to proving this lower bound lies in a clever construction based on the Choi-Lam form. Now, this form is a bit of a celebrity in the world of polynomials. It's a non-negative polynomial that refuses to be written as a sum of squares.
Wait a minute, I thought all non-negative polynomials could be expressed as sums of squares. Isn't that the foundation of SOS methods?
That's a common misconception. While it's true, for many cases, the Choi-Lam form is a classic counterexample. It's a non-negative polynomial that simply cannot be represented as a sum of squares.
So it's a rebel in the polynomial world.
Exactly. And we're going to use this rebel to construct a specific 5-variable polynomial, which we'll also call tally now. This polynomial is essentially the Choi-Lam form in disguise, viewed as a 5-variable polynomial with an additional variable u that doesn't actually appear in the expression.
So it's like we're introducing a phantom variable.
Precisely. The reason for this trickery will become clear soon. The important point is that the maximally symmetric matrix representation of this 5-variable polynomial, denoted as Q, will inherit the non-sum of squares nature of the Choi-Lam form. It will have a block structure with a 0 block corresponding to our phantom variable.
Okay, so we've constructed this special polynomial and its matrix representation. How do we use it to prove the lower bound?
We're going to focus on a specific principal submatrix of the matrix GR. This GR matrix appears in the definition of the spectral bound, but shifted by a term involving The absolute value of the spectral bound multiplied by the matrix Mr. Corlea. We'll call this submatrix H.
So we're zooming in on a specific part of GR and analyzing its properties.
Exactly. And the choice of this submatrix is strategic. By carefully examining the structure of H and using the properties of the Choi-Lam form, we can show that it can be expressed as the sum of two matrices. One involves the maximally symmetric matrix representation of the original Choi-Lam form, and the other involves the projection matrix onto the symmetric subspace of four variable polynomials.
Okay, we've expressed H as the sum of two special matrices. What's the next step?
The magic happens when we exploit the fact that H must be positive semidefinite. Using this property, along with some inequalities involving the matrix M, we can derive a lower bound on the absolute value of the spectral bound.
And what does this lower bound tell us?
It reveals that the spectral bound cannot decrease faster than 1R2. In other words, the convergence rate of the spectral hierarchy is lower bounded by 1R2.
So we've hit a fundamental limit. No matter how much we try, we can't get a convergence rate better than O1R2 for the spectral hierarchy. The Choi-Lam form really set a boundary here.
Exactly. It's a beautiful example of how a seemingly abstract mathematical concept can have profound consequences for the performance of optimization algorithms.
So we've established the best possible convergence rate for the spectral hierarchy. But what about the banded real de Finetti theorem? Does this lower bound for the spectral hierarchy imply anything about the limitations of the banded theorem?
It does. Remember, we used the banded real de Finetti theorem to analyze the spectral hierarchy. So our lower bound for the spectral hierarchy implies a corresponding lower bound for the approximation error in the banded real de Finetti theorem. Essentially, we can construct a specific unit vector for which the approximation error in the banded theorem is also lower bounded by A1R2.
So the banded theorem also has a fundamental limit in its approximation capabilities.
Precisely. We can't expect to achieve an arbitrarily fast convergence rate when approximating real doubly symmetric matrices using this theorem.
It seems like these lower bounds are highlighting the inherent challenges of working with real-valued objects in this context.
You're absolutely right. These lower bounds aren't just abstract mathematical curiosities. They provide valuable insights into the limitations of our tools and help us set realistic expectations for performance.
Okay, we've covered a lot of ground. We've explored the convergence analysis of the spectral hierarchy, proved a fundamental lower bound, and even uncovered implications for the banded real de Finetti theorem. What a journey. But before we move on to the final part of our discussion, I'm curious about the bigger picture. We've seen this fascinating interplay between polynomial optimization and quantum information theory. Is this just a coincidence, or is there something deeper at play? It does feel like we've stumbled upon this hidden connection between these two seemingly distinct fields.
It's more than a coincidence, I believe. Both polynomial optimization and quantum information theory are fundamentally concerned with representing and manipulating complex systems. In polynomial optimization, we're trying to find the optimal value of a function, often under various constraints.
And in quantum information theory, we're dealing with the complexities of quantum states, entanglement, and all the fascinating phenomena that arise in the quantum world.
Exactly. Yet the mathematical tools developed in one field often prove surprisingly useful in the other. For instance, the idea of representing a polynomial as a sum of squares has deep connections to the concept of representing a quantum state as a density matrix. These seemingly different concepts share a common mathematical structure.
It's like discovering a hidden passageway connecting different realms of mathematics.
Precisely. And the quantum de Finetti theorems are a prime example of this cross-pollination. They were initially developed for handling the complexities of quantum states, but now we're finding they have remarkable applications in analyzing classical optimization algorithms.
So this connection is more than just a fleeting similarity. It suggests a deeper mathematical unity underlying these fields.
Absolutely. And as we continue exploring these areas, we're likely to uncover even more surprising connections and powerful tools that bridge the gap between the classical and the quantum.
This has been an incredible journey. But, like any good adventure, it has to come to an end. Before we wrap up, though, I'd love to hear about some of the open questions and future directions that you're most excited about.
There are so many intriguing avenues to explore. But let's start with the banded real de Finetti theorem. We know its convergence rate is lower bounded by that 1R2, and we have an upper bound of our 1R, but the exact convergence rate remains a mystery.
So there's still a gap in our understanding.
Exactly, and closing that gap would be significant. It would give us a more precise understanding of the approximation capabilities of this theorem and its implications for analyzing real-valued optimization problems.
What about the Moment-sos hierarchy? We discussed the impressive O1R2 convergence rate achieved by Fang and Fauzi. But is that the best possible rate?
That's another exciting open question. We currently only have an upper bound. It's possible that the Moment-sos hierarchy has a hidden speed boost that we haven't yet discovered. Proving a tight lower bound for this hierarchy would be a major breakthrough.
It's like we're wondering if there's a turbo button on the Moment-sos engine.
Precisely. And finding that button would be a game changer.
Well, on that note, we've reached the end of our deep dive. Thank you for joining us on this incredible journey through the world of polynomial optimization and quantum information theory.
It's been a pleasure sharing our insights with you. Keep those thinking caps on and never stop exploring the fascinating world of mathematics.
Until next time, may your mathematical adventures be filled with wonder and discovery. Welcome to another deep dive. Today we're going to be looking at polynomial optimization on the unit sphere.
Okay.
Specifically, we're going to be focusing on the concept of proof in mathematics.
Right.
You've given me some really fascinating sources that explore this in detail, and I'm excited to unpack them with you.
Yeah, sounds good.
Okay, so let's set the stage.
Okay.
The core problem here is finding the minimum value of a polynomial on the unit sphere.
Right.
Now, this sounds pretty simple.
Yeah.
But actually, the source material indicates that it's got these really deep connections to a bunch of different fields.
Absolutely. Yeah, this problem, it kind of pops up everywhere. Optimization and quantum information theory, signal processing. It's really all over the place.
Wow. So it's kind of a fundamental problem.
Yeah, you could say that.
Okay, cool.
Yeah.
So the sources you've given me explore two main approaches to tackling this problem.
Right.
The Moment-sos Approach and the Spectral Approach.
Exactly.
And each of those uses different mathematical tools to construct bounds on the minimum value.
Yeah, that's right.
We've got the semidefinite bounds from the Moment-sos Approach.
Yeah.
And we've got spectral bounds from the Spectral Approach.
Exactly. And what I think is really interesting is that the sources that you've shared, they dive into the convergence analysis of these bounds.
Right.
So they look at how quickly these methods can get us close to the true minimum as we put more and more computational effort into it.
Yeah. And that's where the concept of proof comes in.
Exactly.
The sources mention things like the polynomial kernel method
Yeah.
and something called quantum Finetti theorems, which I've got to say sound a little intimidating.
Yeah, they sound a little scary, but
Yeah.
they're really not that bad once you
I
get
guess
to know them.
I'm eager to hear how it all kind of fits together.
Yeah, for sure. So let's maybe start with this polynomial kernel method.
Okay.
So it's this really neat trick or technique for analyzing functions. And in this case, it turns out to be really useful for proving the convergence rates of these optimization methods.
Yep.
So imagine you have a photographer and they're using a special filter to kind of enhance details in an image. The polynomial kernel method, it kind of does something similar. It uses a carefully chosen polynomial to filter our optimization problem.
Okay.
And by doing that, it kind of pulls out key properties that are helpful for understanding how quickly it converges.
That's a really interesting analogy.
Yeah.
So how does that actually work, like in the context of, say, the Moment-sos Approach?
Yeah.
Because the source kind of dives right into the mathematical details and it gets pretty dense.
Yeah, it is pretty heavy going.
Yeah.
But let's try and break it down into pieces.
Okay.
The first thing we do is we represent our polynomial as a matrix.
Okay.
This is pretty standard in optimization.
Right.
And it lets us use all the tools of linear algebra.
Okay.
Then we apply this polynomial kernel method.
All right.
And what that means is we convolve this matrix with our chosen kernel.
So we're convolving the matrix.
Mm-hmm.
What does that actually do?
So you can think about it as transforming the matrix into a form.
Okay.
Where we can analyze its properties more easily. The convolution process, it's guided by this carefully chosen kernel.
Okay.
And it brings out certain features of the matrix that are connected to the convergence rate.
So it's like highlighting the convergence information in the matrix.
Exactly. And once we've transformed it, we can analyze this transformed matrix very carefully.
Okay.
And by doing so, we can establish bounds on how quickly the Moment-sos approach converges to the true minimum.
Wow, that's really interesting.
Yeah.
So to get these bounds, we rely on something called quantum Finetti theorem.
That's right.
It sounds a little intimidating.
Yeah, I mean, it's got quantum in the name, right?
Yeah.
It sounds kind of scary, but the main idea is actually pretty intuitive.
Okay.
So these quantum Finetti theorems, or QDF theorems for short,
Right.
they're powerful tools for understanding the behavior of symmetric states in quantum mechanics.
Okay.
And they have this really neat connection to our optimization problem.
Okay, I'm intrigued. how do these quantum theorems apply to finding the minimum of a polynomial?
So the key is the connection between symmetric matrices and these symmetric quantum states.
Okay.
So remember how we said we're representing our polynomial as a matrix?
Yeah.
And in the Moment-sos approach, this matrix is symmetric.
Right.
This is where the QDF theorem comes into play.
Okay.
It lets us approximate this symmetric matrix using a simpler form that's much easier to work with.
So we're simplifying the problem by connecting it to this quantum world.
In a sense, yeah. So we can leverage this QDF's theorem to connect the properties of our original matrix to the simpler structure of these approximated states.
Okay.
And this makes it a lot easier to analyze the convergence.
That's really clever.
It is. It's a neat trick.
So the source mentions that there are different versions of the QDF theorem.
Right.
One for complex matrices and another for real matrices.
Yeah.
Why does that matter in our case?
Well, it matters because we're dealing with real polynomials, which means the matrices that we're dealing with have real entries. And the source specifically says that we need a QDF theorem that's tailored for real matrices.
Okay, so we need to make sure that our analysis is valid in the real world.
Exactly. We don't want to use complex numbers when we don't need to.
Right. It would just introduce a whole bunch more complexity.
Yeah, it would be like trying to fit a square peg in a round hole.
Right. You want to use the right tool for the job.
Exactly. We need the right tool for the job.
Okay.
And so the source, it points to this real version of the QDF theorem that was developed by Doherty and Wiener.
Okay.
And this theorem applies to what they call maximally symmetric matrices.
So these matrices, they have a special structure where everything's really related.
Yeah, that's right. They're highly symmetric. You can think of it like a perfect snowflake.
Okay.
Where each branch is a mirror image of the other.
I'm starting to get a visual.
Okay, good. So this Doherty and Wiener QDF theorem, it helps us approximate a very specific part of these snowflake matrices. Something called the symmetrized partial trace.
Okay, so how does that connect back to analyzing the convergence of the Moment-sos approach?
Right, so this is where it gets interesting.
Okay.
This approximation, it allows us to connect the complex behavior of our original matrix to the simpler properties of these symmetrized partial traces, which are much easier to analyze. And by doing this, we can actually prove the convergence rate of the Moment-sos bounds.
So we're using this quantum de Finetti theorem as a bridge.
Yeah, like a bridge.
To connect the complex world of the polynomial to the simpler world of these special traces.
Exactly. It's really cool how these seemingly abstract mathematical concepts are all interconnected.
It is. I've got a confession to make, though.
Okay.
I'm still a little fuzzy on why we're making this distinction between real and complex numbers.
Okay.
Isn't math just math? Like, why do we need these separate quantum de Finetti theorems for real and complex matrices?
It's a great question, and it really gets to the heart of why we need to be very careful about the types of numbers that we're using.
Okay.
So math might be this universal language.
Yeah.
But the rules can actually change a little bit depending on whether we're dealing with real or complex numbers. And for this optimization problem, sticking with real numbers is super important. Because ultimately that reflects the applications that we're interested in.
So it's about grounding the math in reality.
Exactly.
Can you give me a concrete example of why a complex QDF theorem might not be enough when we're dealing with real polynomials?
Sure. Yeah, the source actually gives a really nice counterexample that illustrates this point perfectly. It shows that if you just take the standard quantum de Finetti theorem for complex matrices and try to directly apply it to real matrices, it just doesn't work.
Oh, wow.
You get contradictions. You can't guarantee the same convergence properties.
So we really need to make sure that we're using the right tool.
We need the right tool for the job.
Okay, that makes sense.
Yeah.
So we need this real version of the QDF theorem.
Right.
Okay. But now I'm curious about the spectral approach.
Okay.
Because the source also talks about its convergence analysis.
Yeah.
And it seems like there are some key differences there compared to the Moment-sos approach.
Yeah, you're right. The spectral approach, it relies on different mathematical tools.
Okay.
Mainly something called eigenvalue computations.
Okay.
And the convergence analysis involves a different flavor of QDF theorems.
Okay, so let's dive into that in part 2. This is getting really interesting.
Yeah, let's do it.
All right, so we talk about the Moment-sos approach and its convergence analysis.
Right.
Now let's turn our attention to the spectral approach.
Okay.
The source material mentions that it actually uses a different type of quantum de Finetti theorem.
Yeah.
It seems counterintuitive because it's for complex matrices.
No.
even though we're dealing with real polynomials. Why is that?
It is a bit surprising, I guess, but there's a good reason for it. The spectral approach, remember, it relies on these eigenvalue computations.
Right.
And these computations, they're generally a lot faster than the semi-definite programming that you use in the Moment-sos approach. And the existing quantum de Finetti theorem for complex matrices,
Right.
particularly the one for doubly symmetric matrices.
Okay.
It's just a really powerful tool
All right.
for analyzing the convergence of these spectral bounds.
Doubly symmetric matrices.
Yeah.
We talked about Maxwell symmetric matrices before.
Right.
Are these the same thing?
They're related, but not exactly the same.
Okay.
So remember that snowflake analogy?
Yes.
A maximally symmetric matrix is like that perfect snowflake where every branch is a mirror image of the others. A doubly symmetric matrix got a little bit less restrictive symmetry.
Okay.
It's more like a butterfly,
Okay.
where the two wings are mirror images of each other.
So the complex quantum de Finetti theorem for doubly symmetric matrices,
right.
that gives us a way to connect our real optimization problem to a complex one.
Yeah, it's like taking a detour
Okay.
through a more familiar landscape
Yeah.
to reach our destination faster.
I like that analogy.
But the source points out that this detour, it does come with a challenge.
No, what's that?
We have to make sure we can translate the results back to the real domain.
Yeah, we can't just be jumping back and forth between real and complex numbers.
Exactly. We got to be careful.
Okay, the source mentions that researchers had to develop these intricate techniques
Yeah.
to ensure the accuracy of the bounds
Right.
that were obtained through this complex detour.
Exactly. It's all about striking a balance. You want to harness the efficiency of the complex domain, but you got to make sure that your results are still accurate.
Right, they reflect the real polynomial.
Yeah, the source highlights the work of Lovitz and Johnston.
Okay.
They developed this really rigorous framework for analyzing the convergence
Okay.
of spectral bounds using this complex QDF theorem.
Their work seems to be pretty influential.
Yeah, it's very influential.
The source mentions that they introduced this new hierarchy of spectral bounds.
Right.
And a clever way to analyze their convergence.
Yeah.
Can you break down their approach a little bit further for me?
Yeah, sure. So they start by constructing a sequence of spectral bounds that get tighter and tighter,
Right.
meaning they get closer and closer to the true minimum value.
Okay.
And then they cleverly connect these bounds to a specific type of QDF theorem
Okay.
for complex matrices. And this allows them to analyze how quickly the bounds converge.
So we've got this hierarchy of bounds,
Right.
each one getting closer and closer. And the QDF theorem tells us how fast they're getting there.
Exactly.
How does the QDF theorem actually work in this context, though?
So the key idea is that this theorem, it lets us approximate a specific part of our doubly symmetric matrix.
Right.
Remember the symmetrized partial trace?
Oh, yeah, we talked about that before.
Yeah, it's the same concept.
With the Moment-sos.
Right. But the details are a bit different.
Okay.
And how it's used in the analysis is a little different as well.
Okay.
But the main idea is the same.
So we're kind of simplifying the problem
Yeah.
by connecting it to the quantum world.
Exactly. We're leveraging these quantum theorems to bridge the gap between the complex polynomial and the simpler properties of these approximated traces.
So it makes the analysis easier.
Yeah, a lot easier.
Okay, so we've got the complex QDF theorem.
You're right.
It helps us analyze these spectral bounds. But the source also mentions some limitations.
Yeah.
Challenges that arise when we go back to the real domain.
Right, when we translate back.
Yeah, can you elaborate on those a bit?
Sure. So one of the biggest challenges is making sure that the bounds that we get from this complex optimization problem, they're actually still accurate when we bring them back to the real world.
So it's like a tightrope walk.
It is a balancing act.
Between the efficiency of the complex domain and the reality of our polynomial problem.
Exactly. We got to make sure that we don't lose any important information along the way.
And that's where Lovitz and Johnston's work is really important.
Yeah, they did some amazing work.
They were able to navigate these complexities and establish this really robust framework.
Right.
Now, the source mentions that the spectral approach, while it's generally more efficient computationally than the Moment-sos, it might sacrifice some accuracy in the bounds.
Yeah, that's true. There is a trade-off.
Okay, can you elaborate on that?
Sure. The Moment-sos approach.
Okay.
Remember, it uses semi-definite programming.
Right.
It tends to produce tighter bounds.
Okay, so it's closer to the real minimum value.
Yeah, exactly. But this comes at a cost.
Okay.
Computationally, especially when you're dealing with really big, complicated polynomials.
So it's slower, but more accurate.
That's a good way to put it. You can think of the spectral approach as a shortcut.
Okay.
It's faster,
Uh-huh.
but it might not be quite as precise.
Right. And which approach you use really depends on the specific problem.
Exactly. Depends on what you're trying to do.
This is all incredibly insightful.
Glad you're enjoying it.
But the source mentions something else that's really interesting.
What's that?
A banded real Finetti theorem.
Yeah.
And this could be a real game changer.
It could be.
Can you tell me more about that?
Yeah, so what's really exciting about this banded theorem
Okay.
is that it gives us a more direct path
Okay.
to analyzing the convergence of spectral bounds for real polynomials.
So it's getting rid of that complex detour?
It cuts out the middleman, exactly.
Wow. So it's a major simplification.
Yeah, it's a big deal.
How does it actually work, though?
Okay, so the banded part
Okay.
refers to the fact that this theorem applies to a special type of matrix,
Uh-huh.
doubly symmetric matrices,
Right.
but the non-zero entries, they're all concentrated along a diagonal band
Okay.
around the main diagonal.
So it's like we're focusing on this specific region.
Exactly. We're zooming in
Okay.
on this band where the symmetry holds,
Okay.
and we're applying a special QDF theorem.
So a specialized tool
Right.
just for that region.
Yeah, just for that band.
Okay.
And this might sound like it's only useful for a very limited set of problems.
Right.
But actually a lot of optimization problems
Okay.
can be formulated in a way
Okay.
that leads to these banded, doubly symmetric matrices.
Interesting. So it has real-world applications.
Yeah, absolutely.
The source material even mentions that this banded theorem
Yeah,
could lead to more efficient algorithms,
that's right.
specifically tailored for real polynomial optimization.
Exactly. Because it simplifies the analysis so much.
Okay.
It makes it easier to design algorithms
Right.
that exploit the structure.
Wow, this banded theorem is sounding pretty important.
It's a big...
It's more than just like a small step forward.
Right. It's a pretty big leap.
It's like a fundamental shift
Yeah, you could say that.
in how we analyze these spectral bounds.
I think so.
We've talked about the Moment-sos Approach, the
Yeah.
Spectral Approach,
Yeah,
this complex quantum Finetti theorem detour,
right.
and now this banded real QDF theorem.
It's a lot to take in.
It is a lot.
But I think it just shows how many clever ideas are out there in this field.
It's really incredible.
It's a beautiful area of math.
So we've been talking about convergence analysis this whole time.
Right.
How quickly do these methods actually find the minimum?
Uh-huh.
But is there a limit to how fast they can converge?
That's a great question.
Like, is there a speed limit on our mathematical highway?
It's a very deep question.
Yeah.
And it gets to the heart of what we call complexity theory in mathematics. And the source actually addresses this by introducing the concept of a complexity lower bound.
Oh, right. The lower bound.
Yeah, the speed limit.
It tells us we can't go any faster.
No matter how hard we try.
What does the source say about this lower bound?
So specifically for the spectral approach,
Okay.
the lower bound for the convergence rate is something called big omega of 1 over r squared.
Big omega 1 over r squared.
Yeah, that's right.
Okay, so no matter how clever our algorithms get,
Right.
we can't expect them to converge any faster than that.
That's the limit.
Wow, so there's this fundamental limit.
Yeah, it's baked into the problem itself.
Wow. Okay, what about the Moment-sos approach?
That's a good question.
Does that have a known lower bound?
Unfortunately, the source doesn't give us a definite answer.
Okay.
It's still an open question.
So there's still a mystery to be solved.
There you go. Something to work on.
That's exciting.
It is. It's cool that even in an area like this,
Yeah.
where we know so much,
Right.
there are still unanswered questions.
So for the spectral approach, we have this proven convergence rate of big O of 1 over r.
That's right.
But we also know that it can't converge any faster than big omega of 1 over r squared.
Right.
And for the Moment-sos approach,
Yeah.
we know that it converges at a rate of big O of 1 over r squared. But we don't have a proven lower bound yet.
It's still a mystery.
So there are these gaps
Yeah.
between what we know
Yeah.
and what we don't know.
Exactly. And those gaps, they represent areas of active research.
Right? People are working on this stuff right now.
Absolutely.
That's pretty cool.
It is. It keeps things interesting.
So before we move on, I want to touch on something else that the source mentions.
Okay.
It's called the butterfly factorization.
Oh, yeah.
And it seems to be connected to this banded real QDF theorem.
It is. There's a cool connection there.
Can you tell me a little bit more about that?
Sure. So the butterfly factorization.
Okay.
It's this technique
Uh-huh.
that's used in signal processing
Okay.
and numerical analysis
Okay.
to represent certain types of matrices efficiently,
Okay.
particularly those with the banded structure.
So it's kind of tailor-made.
Yeah, it works really well for
It's
those.
this type of matrix.
Yeah, and it turns out that it plays a key role
Okay.
in the proof of the banded real QDF theorem.
So it's a tool from another field
Yeah, it's borrowed from another area.
that has a new application here.
That's right. Math is all interconnected.
How does it fit into the proof, though?
So the proof relies on carefully constructing a sequence of approximations
Okay.
to the target matrix
Right.
and the butterfly factorization.
Right.
It gives us a way to represent these approximations
Mm-hmm.
in a really compact way
Mm-hmm.
that's also computationally efficient.
So it makes the proof easier to manage.
That streamlines things, yeah.
So it's like the scaffolding for the proof.
It's a good analogy.
Okay, so this butterfly factorization,
Right.
it helps unlock a deeper understanding of these spectral bounds.
It does.
This whole deep dive has been incredible.
I'm glad you think so.
We've gone through the intricacies of polynomial optimization on the unit sphere.
It's a mouthful,
It is.
but it's fascinating.
It is. We've explored the different approaches,
Yeah.
their power and limitations.
Yeah.
We've delved into these quantum de Finetti theorems.
Right, they're pretty wild.
They are.
Once you get into the details.
And we've even talked about some cutting-edge research.
The bleeding edge.
It's really pushing the boundaries of this field.
Yeah, it's an active area.
I feel like I have a whole new appreciation for math now.
Me too.
It's so beautiful and deep and interconnected.
Couldn't agree more.
So for our listeners who might be feeling a little overwhelmed right now,
Understandable.
what's the one key takeaway that you'd like them to remember from all of this?
I think the most important takeaway is that even in a field as complex as this,
Okay.
the quest for understanding,
Yeah.
for finding those optimal solutions,
Uh-huh.
it all boils down to these fundamental mathematical principles.
Right.
And the journey might be tough,
Yeah.
but the rewards are huge,
Okay.
both intellectually
Yeah.
and in terms of the applications.
I completely agree with you there.
Good.
So as we wrap up this part,
Okay.
I want to leave our listeners with a final thought to ponder.
Fire away.
If these optimization methods are constantly being refined,
Yeah.
if mathematicians are always pushing the limits,
Uh-huh.
what might the future hold?
It's a good question.
What new breakthroughs?
Yeah.
What new applications?
Who knows what's out there?
It's really exciting to think about.
It is. It's what keeps me going.
I'm with you there. This banded real de Finetti theorem sounds like a pretty big deal.
It is. It's a pretty significant development.
Can you unpack it a little bit for me? What makes it so unique?
Sure. So what's really exciting is that it offers us a more direct way to analyze the convergence of these spectral bounds
Okay.
for real polynomials.
Uh-huh.
So remember how we talked about that complex quantum de Finetti theorem
Yeah.
and how we had to kind of take this roundabout route?
Right. A detour?
Yeah, a detour through the complex domain.
Okay.
This new banded theorem, it bypasses all of that.
So it cuts out the middleman.
It does. It gives us a much more intuitive and streamlined proof.
That's awesome.
Yeah.
But how does it actually work?
All right, so the banded part.
Okay.
It refers to the type of matrix that this theorem applies to.
Uh-huh.
So it's still these doubly symmetric matrices,
Okay.
but the non-zero entries,
Yeah.
they're all concentrated along a band.
Okay.
Or you could say a diagonal
Okay.
around the main diagonal of the matrix.
Okay. So it's like we're zooming in on this band.
Exactly. We're focusing our attention on
yeah.
this specific region
Uh-huh.
where the special symmetry holds.
Right. And then we can use this tailored QDF theorem.
Exactly. It's like we have the specialized tool designed just for that region.
Does that mean it's only applicable to a very specific set of problems?
Well, it might seem that way,
Yeah.
but it turns out that a lot of practical optimization problems
Uh-huh.
can actually be formulated
Okay.
in a way that leads to these banded doubly symmetric matrices.
Oh, wow. So it's not just theoretical.
No, it has real-world applications.
That's pretty amazing. The source material even suggests that this banded theorem
Yeah,
could lead to the development of even more efficient algorithm.
absolutely. By simplifying the analysis,
Okay.
it opens up all sorts of possibilities.
Wow, this banded theorem is sounding like a pretty big game changer.
Yeah, it's a pretty significant development.
So it's more than just an incremental
The
improvement.
fundamental shift.
Wow. Okay, so we've talked about all these different approaches.
Right, we've covered a lot of ground.
The Moment-sos Approach, the spectral approach, this detour through the complex QDF theorem,
All right.
and now this exciting new banded real QDF theorem.
It's a lot.
It is a lot, but I think it really highlights
Yeah.
the ingenuity and cleverness of the mathematicians working in this field.
Oh, absolutely. It's a really exciting area of research.
So we've been focusing a lot on this idea of convergence analysis.
Right. How fast can we get to the solution?
Exactly. But I'm wondering, is there a limit to how fast we can go?
That's a great question, and it gets to this idea of a complexity lower bound.
Right, that speed limit.
Yeah, exactly. So for the spectral approach,
Okay.
we know that the lower bound for the convergence rate is big omega of 1 over r squared.
Okay, so we can't go any faster than that.
Nope, that's the hard limit.
No matter how much we optimize our algorithms.
It's a fundamental constraint.
What about the Moment-sos approach?
Ah, good question.
Does it have a known lower bound?
That's still an open problem, actually.
Oh, wow, so there's still a mystery to be solved.
There you go. More research to be done.
This is fascinating. I love that even in a field like this, where we know so much, there are still these unanswered questions.
Yeah, it's what keeps things interesting.
So for the spectral approach, we have this proven convergence rate of big O of 1 over r. But we also know that it can't go any faster than big omega 1 over r squared.
Right.
And for the Moment-sos approach, we know it converges at a rate of big O of 1 over r squared.
Yeah.
But we don't have a lower bound yet.
So there's a gap there.
Right, so we know how fast it can go, but we don't know how slow it has to go.
Exactly. That's what we're trying to figure out.
That's incredible, and it's all happening right now.
Yeah, it's an active area of research.
This entire deep dive has been eye-opening.
Glad to hear it.
We've explored the intricate world of polynomial optimization. We've delved into the complex realm of these QDF theorems.
And their real counterparts.
Yes, and we've even glimpsed the future with this banded real quantum de Finetti theorem.
Pretty amazing stuff.
It's really remarkable how these seemingly abstract mathematical concepts have such tangible real-world applications.
Yeah, the connections are everywhere.
So for our listeners who might be feeling a little overwhelmed by all of this,
Understandable.
what's the one key takeaway you'd like them to walk away with?
I think the most important thing to remember is that even in a field as complex as this, it all boils down to these beautiful, fundamental mathematical principles.
Yeah, and while the journey might be challenging,
Uh-huh.
the rewards are incredible.
Absolutely.
So as we wrap up this deep dive, let's leave our listeners with a final thought. To ponder if these optimization methods are constantly being refined and mathematicians are always pushing the boundaries, what might the future hold? What new breakthroughs and applications await us? It's a question that really fills me with a sense of wonder and excitement.
And that sense of wonder, that's what drives us to explore, to discover, and to uncover the hidden beauty of mathematics.
Thank you for joining us on this incredible journey into the world of polynomial optimization on the unit sphere. Until next time, keep exploring and keep that sense of wonder alive.
See you next time.